Good morning, everyone. I welcome you to the day 2 of our 2 weeks joint FTP on system methodologies. I request Padmanabhan sir to kindly start the session.
Thank you, madam.
Yeah.
Good morning, everyone. I'll share the screen.
Yes, sir. You shared the material yesterday, sir?
Yeah, I shared the material yesterday.
Yes, everyone, you can check back in your drives after the session. Sir has already shared the day 1 material in that. So let's start.
Good morning, everyone. Welcome to second day of the FDP program. I will explain about the agenda for today's thing. We will have a quick recap of the Quartus tool flow. And then we'll understand about the DE SIM, which is again a remote console hardware. We have seen the remote lab setup yesterday. So this is an extension of that, which is a DE SIM, which requires only the model SIM simulator. And then we will understand the concept of timing analysis and how are we going to apply timing constraints to a design for a pure combinational logic block and for a sequential logic block. How are we going to achieve the timing closure? How do we ensure that the design is not having any setup or hold violations? And then we have a topic on clock domain crossing, which is called as CDC. Let me spend some time in understanding the logic of Quartus. We will have a recap session now. And what is the flow? And we have to constrain the design today. So how are we going to apply the pin constraints and how are we going to apply the timing constraints? We will understand that in detail during the compilation process. And then we will close the timing of our design and then we will configure the design onto the board. So yesterday we have seen how to create the design and now we will understand how to constrain the design and then we will compile the design and we can close the timing for that design. That means we are going to check whether the design is having any violations, either it has setup or hold violations. And we can configure the design onto the board. So we all knew that the Quartus Prime design software is the tool which is used for FPGA as well as SoC system on chip, which we are going to discuss in detail tomorrow with the Cyclone 5 devices. So we have seen the process of synthesis and then it performs a debug, optimization, verification and simulation. So we have seen how we can simulate the design. I showed you an example of how we can perform functional simulation. And then we can take either the HDL or schematic. So in this flow, we are going to take HDL. Either it can be a Verilog HDL or it can be a VHDL. And we can determine how many lookup tables it takes and how many FPGA resources it has taken that we have seen in the compilation report. There are multiple formats to program an FPGA, but then what we are going to use in this class is the SRAM object file. That is the .sof file. That's what we are going to use. So as discussed yesterday, we have a project navigator window, and then you have a tasks window where we can see the compilation process, what happens in each and every step. And then we have a files window where we can develop our own Verilog or VHDL files. We can create our own Verilog, VHDL and system Verilog files. And then we have an IP catalog tab where you could able to see all the intellectual property information here. And then you have a message window where you could able to see any errors or warnings that has been generated. So you could able to see the project navigator shows the project hierarchy, your source files, design units, IP and design revisions in your project. And the tasks window shows the status of the design and it can be used to run or rerun the parts of the design flow. And messages window outputs messages from each process of the run. And then you have a files tab which has tabs for the report browser. We can click open design or we can create a new project. I showed you both methods yesterday. You can create a new project or you can open a project which is already created. And then you have the IP catalog. Let us understand the flow again so that we could understand how do we apply timing constraints and pin constraints to the design. So you have the Verilog or a VHDL code. We perform analysis and elaboration. we do analysis and elaboration to check the syntax errors, and it performs the initial synthesis for us, where the code is getting RTL code, the HTL code is translated into an equivalent gate level schematic. To perform synthesis, then you perform filter, and then you generate the assembler, which is the programming file. Today we are going to perform timing analysis, and then we are going to check whether the design is having any violations or not. So this is the flow we are going to follow. So along with your normal flow, the traditional flow, you should also understand the details of the timing analysis. What is the concept behind timing analysis, and what are the terms and terminologies that are required to perform effective timing closure, that we are going to discuss in detail in today's session. So you could be able to see the quick recap. You take the new project. You can name the project. You can provide the working directory and the top level entity. You can add the source files, and then you can add the device. So as I explained to you earlier, today's focus is also based on Max 10, which we are going to use the DE10 Lite. So the device what we are going to use should be the, we have to filter it with the proper family settings. And then you have the EDA tool settings. So you could able to see in the slide that we use Max 10. Then we have the filter. You could able to see 10M50 DAF484, and then you could able to check the device correctly. Okay, we have to expand the window so that you can see all the fields, and then you have to get the correct part number. I showed you yesterday that getting the correct part number, you have to refer to the manual. You can download the Terasic DE10 Lite manual, and then you can see the exact family device. And the next process what we did yesterday is the pin planning, where I showed you that there are 2 buttons, and then 10 slide switches, 10 LEDs, and then 6 hexadecimal displays in the DE10 Lite board. So we need to know what are the exact pin settings for that particular board. So you have to give the location as well as the voltage, the IO standard that need to be given appropriately. Once the pin planning is done, we can again recompile the design to ensure that okay, all the pin settings are proper, and then we can generate the programming file, and then we could able to program the design. While compiling the design, you could be able to see that there is analysis and synthesis, how much time it takes, filter, placement and routing, assembler generating programming files, and then time quest, we can say timing analysis. So we could be able to see that what is the time taken for that. You could be able to compile your design. So once the design is compiled, you could be able to see that we are going to apply the SDC file, which is called as synopsis design constraints. And we are going to apply the timing constraints today. So for some of the designs, if you are not applying the timing constraints, the tool will give you an error or warning stating that the timing constraints are not applied, or the design is not fully constrained with for the setup logic, and the design is not fully constrained for the old logic. That information, that warning you may get. So it is always recommended to apply the pin constraints as well as the timing constraints in order to achieve the proper timing closure. So once you compile the design, what happens is you need to program your FPGA, where you could able to do the hardware setup appropriately. And then if it shows no hardware, you should go back to your device driver settings and then ensure that okay, it has been installed properly. You can check with your device manager and then configure that USB blaster is appropriately configured, and then you can program the device. Right, so the moment it shows 100% successful, that means you could able to see the output on the board right now. Now, for example, if it is an AND gate or OR gate example, what we have seen yesterday, you could able to modify the settings, modify the switches or the buttons accordingly, and you could able to view the outputs on the LEDs. All right, so this is a quick recap of your the Quartus flow. All right, so you could able to see that we are also need to understand about the DESIM, which is the remote console hardware, which I need to show you. If you go to github.com FPGA Academy, we have a DE SIM, which is a DE series board, because you have DE10 Lite, you have DE1 SoC, like that we have different boards. So if you directly enter into this github.com/FPGA Academy DE SIM, you could able to see that there is a DE SIM tool which we have into account. This DE SIM tool is an interactive graphical user interface showing the features of a DE series board, such as switches, lights, and displays. Yesterday, when we were examining the remote lab feature, we require the board, but for this DE SIM simulator, you don't require the FPGA board with you. You can download this software DE SIM, which requires only the model SIM Intel FPGA Starter Edition to be installed with your Quartus. You don't require the hardware board that need to be connected. So this tool interfaces with the model SIM simulation software. The simulation results affect the lights and the displays in the GUI as opposed to showing the waveforms. So yesterday when I showed the model SIM, we were analyzing the waveforms. But today when we are going to see the DE SIM, we don't want the waveform to be analyzed. Instead, we can be able to see how the switches and the LEDs are changing. So the example what we are going to see is like a switch to LED, where whatever switch I am changing, the slide switches, that corresponding LED should glow. That is the basic thought process. So now this DE SIM simulator has three parts. It has a front-end graphical user interface, which that we are going to see now. And then there is a back-end simulator interface. The moment you modify anything in the front end, automatically the model SIM will be invoked. And there are multiple example projects for you, which will help you to understand all the interfaces that could be possible. So the DE SIM tool requires only the model SIM HDL simulator, preferably one of the model SIM. That means I told you with the Quartus Lite edition, you will get the Intel FPGA Starter Edition. That is sufficient to invoke this DE SIM simulator. All the informations are available here. What you need to download is this releases 2. You can able to see latest release. If you click that, you could able to see that the DE SIM setup.exe, the source code, and the file, everything is available here. Okay. Once you have the Quartus Lite edition along with the model SIM installed, you could able to install this DE SIM software, and then you could able to access that remotely. Okay. This is another kind of remote tool which is available for us. Okay. So let us enter into that. I will just show you a quick demo. I have installed this DE SIM software 1.0. You could able to see that. Okay. Now you could able to see that there are 10 LEDs. Then there are 10 switches. Then there are buttons here, followed by the 7-segment displays. There are 6 7-segment displays. And then you have PS2, parallel ports, VGA display, which are available in the DE series ports. Now, we need to just say open project, because already all the examples are available for you. So just I take one demo example, which is LED to hex. That means whatever switch I am going to change, that corresponding LED is going to glow. That I need to see on the screen. So how that could be possible, we'll say, just select the folder LED hex and say select folder. Okay. The moment you say that you select the corresponding folder and then you say the project hex opened, automatically what will happen? You need to compile the test bench. It is exactly equal to you do vlog and then you will perform vsim, exactly the same case. So vlog you will do the module and then vsim you will do the test bench, right? Exactly in the similar way in the tickle script, you need to compile it one by one. So just I say compile, so it runs in the background. Could able to see that it is compiling the code and the test bench, and then it shows that top level modules, and then it shows compilation successful. Now, once the compilation is successful, I can say start simulation. I click the start simulation here. And now you could able to see that the simulation is getting started. Could able to see it is loading the test bench, loading work TV, and then loading work up. And now it will be connected to the simulator. We will get a message that it is connected to the simulator. So once it is connected to the simulator, what we can do is we could change the switch accordingly, and appropriately we can see which LED is glowing. Now you could able to see that it is showing that connected to the simulator. That means you could able to see the Intel FPGA starter edition model sim is running in the background. So now what I'm supposed to do is I need to check whatever switches I am changing, that corresponding LED is glowing or not, I should see. Please understand that I have not connected any board physically to my laptop. Okay, so I am just changing the switch here. You could able to see that which switch I am changing, corresponding LED is glowing. You could able to see that. Okay, so this is the example of the LED to hex, which the example projects are already available. The only thing is you should have the light version of the Quartus along with that Intel FPGA starter edition model sim is installed. Okay, I can stop the simulation here. Okay, so I will show you one more example. This is one small combinational logic example I showed you. I will just show you one more counter example in the similar platform. And then we will share the link with you so that you could download these informations and then you can set up and then you can try all these examples which are provided in the demo project. So now I say again open project. You could able to see that there are counters. I say counter LPM. So just one counter I will take. Okay, that is the folder I am selecting now. Select folder. So the moment I selected the folder, you could able to see that it was earlier showing connected to the simulator. Now it is showing end simulation and it shows disconnected from the simulator. That means the first project is disconnected from the simulator. Now we can connect the second project to the simulator. I say compile the test bench. Then you can say start simulation. You could able to see that the counter starts counting. I can ensure that okay, this counter is starting the logic. Like this, we could able to see, you can view the details of the Verilog code, what is present inside it. And you can also see how the DESIM software works for you. This is one more remote platform which is available with us, along with what has been described in the earlier session, that is yesterday's session. So I can say stop simulation here, and then I can close this DESIM software. Okay. All right. So now the thought process is you need to see that how that could be useful for us to get into the logic of the DESIM, because that doesn't require a hard board for you. So in the earlier case, you require a DE10 light board that would be connected locally. But for this DESIM software, you don't require it. Another important information is you can go and search for the FPGA boards for the Intel academic program. If you go here, if you search this page, you could be able to see the multiple boards that are available here. You can able to see teaching and project boards. There you have DE1 SoC, you have DE10 standard, and then you have DE10 light. And what is available here, you could able to see that the entire details of this information is provided here. It is not only the user manual, you have data sheets. Then you could able to see that the Quartus setting file, which is called the QSF file. And also it has the synopsis design constraints, which is called as the SDC file. So you could able to see for all the boards, for example, the DE1 SoC, the DE10 standard, or the SoC boards. That means it has the hardcore, dual core ARM Cortex A9 that is also embedded inside the FPGA fabric. Whereas the DE10 Lite, which is the one which we are doing exercise now, you could able to see that the DE10 Lite has all the basic features that are available. But then ideally it is useful for all digital logic exercises. You could able to see because it has 64 MB SDRAM, 6 7-segment displays, and then 10 toggle switches, 10 LEDs, and then you have push button switches. As discussed yesterday, the clock frequency is 50 megahertz. And then you have the built-in VGA, all those informations are there. So this particular logic code is ideal for your digital logic exercises. And then you can able to see embedded and robotic boards, which could be useful for IoT and then other applications. You have a DE10 nano board. And similarly for the research boards, you have DE10 Pro. These are largest boards which are useful for your research applications, which is based on Stratix 10 GX. The other one is on AI10. So whenever you are free, you can refer to this information. You can just go to FPGA boards for the Intel academic program. And then you could able to see that what kind of boards could be targeted for what kind of applications. You have all the details here that are specifically provided. So then there are specific documentations also available, which you could refer. You'll get multiple informations from here. Still you have any doubts, you can contact us. We will guide you accordingly. Okay, right. So now we will enter into the timing analysis session. If there are any questions, please let me know. Otherwise, we'll start discussion with the timing analysis flow. Are there any questions in the chat window? Okay, shall I proceed? Are there any questions?
No, Paddy, I don't think there are any questions, Paddy.
Okay, then I'll go ahead. Thanks, Bhaskar. Let us understand the objectives for today's session. Understand the Quartus timing analyzer, and we are going to understand the timing analysis design flow. And we are going to apply basic and complex timing constraints to an FPGA design. So basic, that means we are going to understand the design is very small if it's a pure combinational logic block. What is the constraint we are going to apply? And then we are going to see the complex timing constraints. That means you are going to apply the clock constraints, the input delay constraints for the input to reg path. And you need to understand how to apply the set output delay constraints for the register to output paths. And then we need to check whether are there any unconstrained paths. We are going to report it. Along with that, we are also going to discuss on the timing exceptions, which we call that as the false paths, multi-cycle paths, and pure combinational paths, which are coming into account. And then we are going to take a design. We are going to analyze an FPGA design for timing using the Quartus timing analyzer. And then we will write and manipulate SDC files. So SDC stands for Synopsys Design Constraints, remember, and QSF stands for the Quartus settings file. So the write and manipulate SDC files for analysis and controlling the Quartus compilation. So we'll recap, seeing the recap of the Quartus tool flow. We have seen that how do we need to apply the pin constraints and how do we need to apply the timing constraints in order to achieve the timing closure. Today we are going to see that how do we apply effective timing constraints to a design. And we are also going to discuss about the need for multiple clock domains and the concept of clock domain crossing. So why there is a need for multiple clock domains and how are we going to tackle the clock domain crossing and what are the different issues and techniques that we will discuss in detail. So let us start with the basics. You could able to see that when you say timing analysis, what we also need to understand, timing analysis is a method of analyzing, debugging, and validating the timing performance of a design. So when we say timing analysis, we have two timing analysis techniques. One is called as static timing analysis The other one is called as dynamic timing analysis, which is called DTA. And what we are discussing here is called as the static timing analysis. That means we don't require any test vectors. We are going to check which is the critical path. So critical path is the path which takes the longest delay. So the STA is going to tell us which is the longest delay. Based on that, we are going to find out which is the critical path, and then we are going to fix that path so that the design should not have any setup or hold violations. So we will understand those terminologies one by one. So before getting into the details, we will analyze the paths here. There are three types of paths here. One is called as the clock path. Means you could able to see there is a clock path which reaches the flip-flop. And then you have a data path. So that means you could able to see this T clock Q, this T combo. Then it reaches the data pin of the flip-flop. You could able to see there is a data path. Then you have asynchronous paths. Directly it comes synchronously. Then there are two types of analysis. One is called as the synchronous clock and data paths. The other one is asynchronous clock and data paths. How are we going to take into account? We will see one by one. So we'll have different paths and different analysis types that are available here. So while performing the timing paths, what is very important for us is to understand what are the start points and what are the end points in a timing analysis logic. When you perform STA, the static timing analysis, what is very important for us is what is the start point and what is the end point. Now you could able to see that the start point means you could able to see it starts from an input and then it ends at the data pin of the register. That means what are the start points? The start points can be input ports or the start points can be clock pin. Means you can start from the input port or you can start from the clock pin. What are the end points in an STA when you say? The one is data pin of the flip-flop. The other one is the output port. What are the start points? The start points are input port and the clock pin. And what are the end points is data pin of the flip-flop and the other one is output port. Now, based on this, we are dividing these timing paths into three data path types. What are those three data path types when we say here? It starts from an input port and then it ends at the data pin of the flip-flop. We call this path as input edge, which is nothing but the input to a sequential element. This is one path we have. It means it starts from an input port, goes through the combinational logic, and ends at the data pin of the flip-flop. You have to stop at the data pin. That is the DP. That is the end point. What are the start points? It can be input or clock pin, but the end point is data pin. Similarly, we have from sequential element to sequential element. Now we call this as a register to register. We call this as reg to reg path, register to register path. Okay, when it is register to register path, it starts here. You could able to see register to register. Then it say here you could able to see T clock to Q plus T combo, and then it reaches the data pin of the flip-flop. You could able to see that. So this is your end point. So you start from the clock and then you end at the data. So we call this as what? Register to register path. So that is described as from sequential element to sequential element. That's what we have seen. What is the third information we should know is called? It starts from the clock pin and ends at the output port. That means you could able to start from here. This is called as register to output. That is from the sequential element to the output. So we call this as register to output. So it starts from here, goes through the combinational logic and ends at the output port. Now you could able to see all these data paths we have described. Along with that, you have the clock paths. So that means this reaches the first flip-flop and then this reaches the second flip-flop. And then you also have the asynchronous paths, which we explained in the earlier slide. Now you could able to see that there are three major data type paths which we need to discuss in detail today. The one is called as input to reg path. Number two, reg to output path, and number three, register to register path. So all these three paths should be constrained. That means we need to apply proper timing constraints for all the three paths in order to achieve effective timing closure. So now we have understood that how do we divide the paths. Okay? So that means in STA, we are dividing the circuit into different number of paths. And what are the start points we have seen is number one is called clock pin. The other one is called as the input port. What are the end points in STA when you say the number one is called data pin of the flip-flop, which is D. Okay. And the other one is the output port. Right. Now, again, we'll get into the fundamentals. We have to check what in timing analysis is the logic of the setup and hold. Now, what we need to check in setup and hold? What are the timing parameters that need to be checked is setup and hold? That means we are going to see two slacks. One is called as the setup slack. The other one is called as the hold slack. So your design should not have any violations. That means the user design should not have any setup violations, and your design should not have any hold violations. Now, what we are ensuring here, the clock and the synchronous signals do not arrive at the register input about the same time. That means we need to understand that what is the definition for setup time and what is the definition for hold time, so that we can ensure that there is no problem of metastability. So the register output does not become unstable, and registers transfers data in a known or a guaranteed behavior. So what is that guaranteed behavior? What is the usual or what is the correct data, and why the data is becoming unstable? All those things we will discuss in detail now. Let us understand the fundamentals here. What is the setup time? Minimum time before the clocking event, the data should be stable. So now that you could able to see, the data should not change between in this window. So this is the setup time and this is the hold time. Minimum time before the clocking event, the data should be stable. The minimum time after the clocking event, the data should be stable. That means inside this particular window, the data should be stable. The minimum time, the data signal must be stable before the clock edge. We call that as the setup. And the minimum time, the data signal must remain stable after the clock edge is we call that as hold. So we have understood both the setup and the hold time definitions here in order to get into the details of the time. Now we enter into the launch edge, which latches the data at the destination register. So we call that as launch edge, and then we call that as okay. So are there any questions in the installation? I could be able to see some questions in the chat window. Is there any questions?
Yes, Padmanabhan sir, there are a lot of queries in the Q&A section. Like, is it
Okay.
possible for someone from your end to answer certain queries in the chat box? Or if you want, you can also answer some of them. Actually,
Fine.
many of them are having issues in installation. Like many people
Okay.
are writing that if they are having issues in installation, whom should they contact?
Okay.
And
Right.
like there are certain questions also, why we use async path, what happens if we use synchronous path?
Right. So it is synchronously. There is always an the logic is you have a synchronous clock paths, and then you also have an asynchronous reset and other things in your design, right? So how are we going to tackle them? That's what we are going to discuss in this session. Okay.
One question is, if my design needs 200 to 400 pins for data processing, then how are we managing this on these FPGA boards?
Different FPGA boards are there with different pins, right? So there are different multiple pin complexities. You have the densities. So you will have multiple IO pins, right? So then we can definitely manage that. There is also a facility of automatically you can place the pins. That facility is also available.
Okay. Does the board has discount under university program student discount? Who is the, okay, this question can be answered later. Altera driver is actually, Padmanabhan sir, people are having issues in installation. If you can ask someone at your end to answer these questions in the Q&A, because people are facing certain problems in installation, like the Vidya ma'am is there, and I see a lot of people. One question somebody is asking is, will latch and launch edge be applicable to 2 or more than 2 registers always?
It is always taken care between the launch and latch, means only between 2 registers. Launch is the first register, source register, and then destination register is called as the latch register. So we are going to perform timing only between 2 successive registers.
Yeah, okay. Padmanabhan sir, can I add you in the WhatsApp group of the participants so that they can ask problems, or suggest me a name whom I can add in the WhatsApp group? So that
Yeah, you can add me. I can help them. So the idea is like the lab manual has been given to them yesterday.
Okay.
If they have any issues in installing and using the USB blaster, download your design to the FPGA, that section they can refer, where they can go to the device manager, and then they could be able to see what are the things, how they configure the USB blaster, and how they can update the device driver software. That is explained in detail in the lab manual, which I shared to them yesterday.
Okay, so everyone, I request you to please follow the lab manual. If you have any queries, I'm adding him. Post your queries in the WhatsApp group. If somebody has already resolved that query, please guide them. And if not, Padmanabhan sir, after the talk, he will be guiding you.
Yeah.
Okay?
Yeah.
Yeah. Okay, sir. Yeah, you please continue, sir.
Thank you. Thank you so much. Yeah. Thank you. Right. So now let us understand what is the data arrival time. Okay, and then we will see what is the arrival time of the data. So you could able to see the data arrival time is the launch edge. T clock, that is the time, the T clock 1 which it takes. Right? This is the delay. The TCO, the T clock to Q, right? This one, the transition time. The T data, how long it takes to reach the destination register. We call this as a data arrival time. So we need to understand this as DAT, which is called as a data arrival time. So we have to come up with 2 components. One is called as the data arrival time, and then the clock arrival time. So based on that, we could identify what is the setup and the hold slack. So what is the data arrival time here? The time for data to arrive at the destination register's D input is called as the data arrival time. Now, what is the clock arrival time that we need to see now? That means you know that the clock reaches the first flip-flop at one time, and the same clock reaches the second flip-flop at another time. You could able to see that there is a skew between the clock arrival. So difference in arrival of the clock between 2 successive registers, we call that as a skew. Now, what is the clock arrival time? That is equal to latch edge, that means your destination edge, plus the T clock. What is the time taken for the clock to reach the second flip-flop? That information we should have. So we require 2 informations. One is called as the data arrival time. That is on the launch edge plus T clock 1 plus TCO plus data. And then we have the clock arrival time, which is latch edge plus. Now we need to come up with the required time. That means we need to have the parameters related to data required time. So what is the data required time? When we say the minimum time required for the data to be valid before the latch edge, so that the data can be successfully latched into the destination register. So the data required time setup is equal to clock arrival time, which is the time taken for the clock reach here, minus the setup, that is the setup time. So minimum time before the clocking event, the data should be ready. When you say before the clocking event means what? You need to perform subtraction. Minus uncertainty. Uncertainty, you will have the jitter components or whatever, where there may be a frequency variation in the clock source and any uncertainties that can also be subtracted. So how do you easily remember this? When you say when it is a data required time which is set up, that means the setup time should be subtracted. When the setup time is subtracted, that means what? We are ensuring that the data is available, stable before the setup. So the data required time setup is equal to clock arrival time minus the setup time minus the setup uncertainty. When it is hold, minimum time after the clocking event, the data should be available. When you say, since it is after, that means you need to add that component. So ensure that the data required time hold is equal to clock arrival time plus TH. You are going to add that TH hold uncertainty. If there is any uncertainty on the hold side, that need to be added. Remember, here you have to subtract the setup time and then you have to subtract the setup uncertainty. Whereas in the data required time on the hold side, you have to add the hold because it is minimum time after the clocking event. So you add it, you have hold uncertainty. Now, based on this, we have to come up with the formula. So what is the formula? Is there are two important informations we have arrived at. One is called as the setup slack. The other one is called as the hold slack. So what is setup slack? When you say, you could able to see it is nothing but required time RT minus AT, which is called as arrival time. So the required time minus arrival time, which is RT minus AT when you do. If the number is positive, then we can say that the timing requirement met. That means if your setup slack is positive, RT minus AT, then we could able to see that the design is not having any violations, so it is met. And the required time minus arrival time is a negative number. That means timing requirement not met, and then therefore the design is not meeting timing. So what we need to understand is, when there is a required time minus arrival time, which is called as an RT minus AT, how do we easily remember this? When you say, on the left hand side, you could able to see there is a minimum data required time. That means you are going to take the minimum value of the required time and then the maximum value of the arrival time. The reverse, when we do, we will get the hold slack. So both extreme conditions, that means the design has to be subjected to test for both setup as well as for hold conditions. You have to check for both. So your setup slack should also be positive and your hold slack should also be positive to ensure that the design is not having any violations. So along with that, your delays may also vary with respect to process, voltage and temperature. The manufacturing process differences, the voltage at which it operates and the temperature. So based on these PVT conditions also, the design may have differences in the timing. The timing parameters may be affected by that also. So how do we again remember the formula here for the hold slack is? So there in this case, it is required time minus arrival time. But then in this case, it is arrival time minus required time. So it is minimum data arrival time minus max data required time. That means it is AT minus RT. When it is AT minus RT, when it is a positive slack, then in that case, the timing requirement is met. When it is negative, then it means that the timing requirements are not met. So we can come to a conclusion that we need to ensure that your setup slack value as well as the hold slack value, both should be positive. So what is the basic thought process here? Yes, you can remember these three lines here when you calculate the slack. So setup slack is nothing but DRT, which is called as the required time RT minus arrival time AT. So required time minus arrival time, if it is a positive number, then we can say that the design is not having any setup violations. Similarly, when it is arrival time minus required time, when it is AT minus RT, then if that is a positive number, then the design is not having any hold violations. But when then it has a negative number, then you could able to see that it is having violations. So how do we easily remember this? First, you can put here DRT minus DAT, and then this DAT you put here DAT minus DRT. Okay. Now it is easy for you to understand that when you put that, here you put min for both, and here you put max for both. So what is the formula here? It will be minimum DRT for the setup logic and minimum DAT for the hold logic. How can you easily remember is just to say DRT minus DAT. So similarly, if you want to write here, just write RT minus DAT and insert D on both sides. Similarly, here AT minus RT and insert D on both sides. After that, the left-hand side should be minimum, right-hand side should be maximum. So min, max you put. You could be able to see that this is the formula that is required for us to calculate the slack for the design. So with this, we can see what is the setup slack, whether that is a positive number, whether the design is having any violations, we can come to a conclusion. Similarly, we have a hold slack. That means you could be able to see that the DAT minus DRT, whether that is having violations. So by analyzing these things, it is easy for us to analyze any circuit. So what you need to understand is, again, the similar principle we should follow, that what are the start points and what are the end points. And we have to ensure that the start points and end points need to be taken into account. And then you should apply the formula in order to ensure the design is not having any violations. Let us try to solve one problem here. Let us take this design. You could be able to see there is a flip-flop, which is called as a launch flip-flop, which is called as a source flip-flop, you can say. The other one is called as the destination flip-flop. Okay, you have a launch flip-flop, source flip-flop, and then you have a destination flip-flop here. Then you could be able to see the top frequency is given 20 nanoseconds, which is the 50 megahertz logic. So for each and every case, you could be able to see there is a minimum value and there is a maximum value. So T min, T max, T min, T max. Then you could be able to see T clock to Q minimum and a T clock to Q max. T min 6 nanoseconds, T max 9 nanoseconds, T min 1 nanosecond, T max 2 nanoseconds. And then here you could be able to see for the delay T min 5 nanoseconds and T max 9 nanoseconds. And for hold 2 nanoseconds and for setup 4 nanoseconds is provided. Now, what we are supposed to do is we need to check whether the setup slack is a positive number. Similarly, we have to check the hold slack is a positive number. So what is the formula we have to analyze and apply here? The setup slack is equal to minimum DRT minus maximum DAT is provided. You could be able to see. Now you could be able to see what is the required time and then what is the arrival time. The minimum data required time and the maximum data arrival time. That's what we are going to apply here. We will note down one by one, and then see, we subtract it and then see what is the value that is provided right now. So please analyze again. When you say that you start from here, that is a clock, then you should end at the data pin of the flip-flop. Similarly, for when it is input edge path, you start from an input and then end at the data pin. Then again, when it is edge to output, you start from the clock pin and end at the data pin. Now, let us consider this one by one. We will be able to see minimum delay along the clock path. First, we will see what are these values. The first one is the clock, which is 20 nanoseconds. Yes, you could be able to see what is the minimum delay along the clock path. So you could be able to see 20 nanoseconds plus the minimum value is 2 nanoseconds that is listed. And then again T min 5 nanoseconds. Again, t min 2 nanoseconds. And then you have to subtract setup time. So minimum time before the clocking event, the data should be stable. That means we are subtracting this now here, setup. So 20 plus 2 plus 5 plus 2 minus 4. Now, on the other side, we have to see maximum delay along the data. So now we have seen the clock path. In the clock path, we have taken the minimum delays here. So 20 plus 2 plus 5 plus 2 minus 4 we did. Now we should take the values that is provided in the data path, which is the data arrival time. Now you could able to see that you are going to take the maximum value on the data arrival time. When you are taking the maximum value, that is called as the worst case delay. What happens here we will see. So which is 2 nanoseconds. And then you have 11 nanoseconds, which is called as the T clock to Q. There are two values you could able to see. T clock to Q minimum is 9 nanoseconds. And the T clock to Q maximum is 11 nanoseconds. You could able to see T max 2 nanoseconds, plus 11 nanoseconds, plus 2 nanoseconds, which is the worst delay. And then you could able to see T max, which is 9 nanoseconds, and then plus 2 nanoseconds. So till it reaches the data pin, what is the value? Everything you have to add now. So we have added from here 2 plus 11 plus 2 plus 9 plus 2. So when you do that, what happens here? You could able to see that 25 minus 26 when you do, it shows minus 1 nanosecond. That means there is a violation. The design is having a setup violation. So we will keep that aside. And then the design should also be subjected for the hold check. We will check that also. And then see what happens. And then what kind of conclusion we can arrive at, we will see one by one. So now in this particular case, you could able to see minimum delay along the clock path, which is called as the minimum data required time, minus the maximum delay along the data path, which is called as the max data arrival time. If you do that 25 minus 26, it shows that minus 1 nanoseconds. Now, when we do this, what happens is, since the setup slack is minus 1 nanoseconds, if we increase the period instead of 20, when we increase the period to 21, what happens is, the design is supposed to work at 50 megahertz. But then when you increase the period to 21 in order to compensate that, and then your setup slack should be 0. Now what happens is 26, right now you could able to see when you make that as 21. So you could able to see 1 by 21, your design is working only at 47.6 megahertz because the design is having violations. Now the same design, when we do for hold, what happens we will see. Now, again remember the formula when we are applying the hold check for the same design. Hold slack is minimum delay along the data path. You are going to take the minimum delay along the data path minus maximum delay along the clock. All the clock paths you should take the maximum delay. Okay, so when you are doing setup analysis, you are trying to do that on the capture edge. Okay, when you are doing the hold analysis, you are trying to do that on the launch edge. Okay, therefore, you are not going to worry about the clock because the clock starts at 0, okay, for the hold analysis. You could able to see the minimum delay along the data path is, you could able to see 1 is written plus 9 nanoseconds, because in the earlier case we took 11. So 1 plus 9 plus minimum value, which is 1, is taken. Plus in 6 and 9, the minimum value is 6, that is taken, plus 1. So from this place to this place, what are the minimum values that are noted down? 1 plus 9 plus 1 plus 6 plus 1 minus, we are going to take the data required time, that is the logic, which is on the clock path. Now listen carefully. Now we could able to see that in between 2 and 3 nanoseconds, we have the maximum value, which is 3 nanoseconds. So 3 plus 9, then 3 and then you could able to see hold. So what I explained to you earlier, when it is setup analysis, the setup time should be subtracted. When it is hold analysis, we have to add the hold time. So you could able to see that the hold time is added, which is 2 nanoseconds. Now you could able to see that 18 minus 17, which is 1 nanosecond. And when you wanted to operate at 50 megahertz, the design is not having any hold violations. That means it is fine. But when the same design needs to be operated at this, you could able to see that there is a violation. So we have to change that into 21 nanoseconds. So you could able to see that in order to do this manually, how long it for us to ensure that the design is not having any violations. Now you can understand that this is done between a register to register path. This is done between one register to another register. So now you could able to see there are multiple registers in your design. You will have n number of registers. So if you do a paper and pencil work for all these things, we can immediately come to a conclusion that it will take a lot of time for us to solve this problem. Okay, so when we need to analyze a pure combinational path, or you need to analyze a path with registers, now you could able to see reg to reg, reg to reg, reg to reg. If you go on finding out what is the timing values, and then we wanted to find out which is the critical path in that specific design. With a paper and pencil exercise, it is very tedious and time consuming. And also, we don't know what is the setup time and what is the hold time and what are the values that are involved. So even someone provides you all the delays like what is being explained in this exercise, it is very tough for us to examine and identify. And there are chances that they are error prone, because sometimes we may not know from where to start and where to end, which delays to be added. So in order to solve that particular issue, we use the STA tool, and then the Quartus timing analyzer helps us to solve this problem. So it helps you to find out which is the critical path. And for your constraints, whether the design is able to meet timing or not, we could be able to identify. So the moment you provide a clock information to the design, you could be able to see that for that specified clock, whether your design is able to meet timing or not, that information could be known to you. So your timing analyzer helps you in order to analyze the design and provide you the specific inputs for us to proceed further. Now you could be able to see what are the options that are provided on the setup side, and also on the hold side. Now let us understand on the Quartus timing analyzer. You could be able to see it is a Quartus timing analyzer. You could be able to see there is a constraints editor where you can apply the constraints, and you can apply the constraints for the pure combinational logic block. You can apply constraints for the sequential logic design. You can apply the clock constraints. You can apply the input to reg, which is called as the input delay constraints, as well as the output delay constraints for the design. There are two timing analyzer flows that could be possible. One is using the tool itself to do the logic. That means you are going to follow the steps one by one, and then you use the timing analyzer. And the timing analyzer integration into the Quartus Prime software design flow. We can enable the timing analysis tool, and then how it works in the design flow, that we can cross verify and check. So the basic thought process is, when we are going to examine a design, and then when that design is having any violations, how are we going to ensure that the design is not having any violations that we should see? And the second information is, how are we going to use the timing analyzer tool effectively, and how do we apply the constraints properly? What are the basic steps that are required for performing timing analysis? You could able to see you are going to generate a timing netlist, and then you have enter SDC constraints, which is called as the synopsis design constraints, or you can constrain the design directly in the console. So I can show you directly how we can apply the constraints in the tickle console. Then you can update the timing netlist, and then you can generate the timing reports. If you wanted to save the timing constraints, you can save the timing constraints. If you don't want to save the timing constraints, we can just leave it optional. So what are the steps? We are going to generate the timing netlist, and we are going to apply the SDC constraints, that is the synopsis design constraints. We are going to update the timing netlist, and then we are going to generate the timing reports, and then we can have save timing constraints, which is optional. Now let us go through the flow. What happens into the design when the design gets synthesized? You synthesize a design in the Intel Quartus Prime project, and then you use timing analyzer to specify timing requirements and configure timing analyzer in Intel Quartus Prime project and perform full compilation. That is, you are going to run the fitter, and then you are going to verify the timing in the timing analyzer. That means you are going to perform the same operation what we did yesterday. But along with that, we are going to open the timing analyzer and check whether the design is verified with the timing analysis and whether it has any setup or hold violation. That means whether is the design free from violations, we have to check it. So that is the step usually we follow in the Quartus timing analyzer. Let us enter into the process. What happens when the design gets synthesized? And then we are going to see what are the steps that are available to perform the timing closure. So once the design gets fitted, you could able to see it performs plan, then place, then route, everything. And then once the design gets fitted, we can perform the timing analysis. The timing analysis process is critically very important for us to ensure that the design is not having any violations to proceed further. The next important thing is how do we analyze the timing reports in a timing analysis design. So the timing results available in both Intel Quartus Prime design software compilation report, and we could also see the same in the timing analyzer GUI. Either you can see that in the software compilation report that is provided by the Quartus Prime design software, or you can check that in the timing analyzer GUI. So it includes more extensive reporting capabilities. You could be able to see post map, that means after synthesis, and then you could also see the timing after post fit. That means after fitting operation also, you could be able to see whether the design is having any violations, whether it is placed and route finally, and then whether it meets the timing requirements what we have provided. That means we have provided a clock frequency, whether it is meeting that frequency or not, that information we have to cross verify and check. Now, when the design has the negative violations, that means it has a negative slack, or we need to analyze the different kinds of summary reports. Then we have a list of commands I will show during the demo. But then you could be able to see that you can report the clocks, you can report the timing summary for setup and hold, and you can check what is the worst class. What is the worst is negative slack. That means when you say that as a worst negative slack, that is for a single path. When it is a total negative slack, that is the sum of all the negative. That means if you have 10 paths and all the 10 paths that sum if you add, that will provide you the total negative slack, which you can check. When it is for setup and for hold, that is for the synchronous paths. And for recovery and removal, we can take that for the asynchronous paths which are available in the design. So we call that as a recovery check as well as the removal check, which is equivalent to setup and hold check for a synchronous design. And we can get the more specific detailed reports that are available. Either you can use the create the tickle commands, or you can do that in the GUI. So use GUI to see report immediately. Use tickle file for repeatability. Right. So I will just we'll just take a break here, and then we'll go to the tool to get into the logic to get a feel of how this tickle constraint is helpful for you. Let us open the Quartus Prime project. Okay, this example is the yesterday's design files have the vanilla code as well as the tickle scripts which has been given to you. So how this tickle enable information will be helpful for you, that we will see with a small example right now. I create a new project wizard and say the new project wizard helps you to create a new project exactly in the similar way what we have seen yesterday. Let us consider that and go ahead. So I say here C drive, and then you say here you can say project underscore new and say naming. You can take information. And then what is the name of the project? The name of the project is switch underscore 2 underscore LED. The example is given to you, shared with you yesterday. So for example, you can take the switch to LED. What is the meaning of that is whichever switch we are changing, that corresponding LED is going to be. So I have just given switch to LED I have provided here. Then you say next. It is asking that the project new timing does not exist. Do you want to create it? You say yes. And then we are going to create the empty project. We are going to create the empty project, that is the new project, by specifying the project files and libraries, target device family, and the EDA tool settings. You can say next. Now we need to add the files if you have. Otherwise, you can give next here and then we can continue since we are going to create a new file. Now, what is the device? As yesterday when I explained to you, which is based on the DE10 light. So you can say that which is Maxton device. And then you could able to see that 10M50, then I say DAF, then 484. Remember the specific device filter. Then you can select the device from here and then say next. Now, if you wanted to select the EDA tool settings, you can select it here. Otherwise, you can do it later. So say next. Now you could able to see the summary, which is the project name, the top level design entity, the family name, which is the Maxton device, and then what are the device values that is provided to you. Then you can say finish. Okay, right. So now you can say it is a Verilog project. So you could able to see it is targeted for 10M50 DAF 484. Now I say file and then say new, and then go to the Verilog HDL file and then say OK. So where this file is located, it is given to you as a design file. You can take that from there. What has been included in these design files is you have the switch to LED Verilog file, then Mux examples, set of Verilog files, and then you have a Night Rider example which I showed you yesterday. The Verilog file is available. Along with that, you have the configuration. So DE10 light pins.tcl. That is sufficient for you. Because you wanted to do pin planning, you need to do the pins one by one. Instead of that, you can use the tickle file from here. Okay, so you can take the switch to LED example from here. I'm going to copy this design and that you can paste it in your status window here. You could able to see that module, switch to LED, switch SW, and then LED R. You could able to see input 9 down to 0 switch, and then output 9 down to 0 LED R. Whatever switch you are going to change, that corresponding LED it is going to change. So you have taken that design right now. Now I need to save this. You can say file, save as, and say switch to LED.v. You can save this here. Now, what is the basic thought process is you are going to analyze and elaborate the design, and then you are going to apply the compilation process exactly in the similar way what we have done earlier. But then what is very important that is you can enable all the pin constraints in the tickle window today. Okay, when you are doing pin planning, what we have done earlier is we have opened the DE10 light, the user lab manual, and then you have gone through what is the pin for each and every logic. Exactly in the similar way we can do it one by one, or you can write this tickle script which helps you to put all the pins automatically. Right? So you could able to see that in the lab manual, it has been given to you that what is the specific thought process for each and every pin that is provided to you. I will show that also for reference. Please remember that. So you could able to see that all the LEDs, their pin numbers, as well as the description is provided. And for all the switches, their pin details and the switches is provided, and the clock frequency details are provided for DE light board as well as for the DE0CV board. So you can use this pin configurations one by one, or else all these things are available as a TIL file for you. So you can directly copy and paste those informations in the TIL console. So since it is a pin constraints, we are going to apply those constraints that we are discussing that. So we need to apply the pin constraints to the design, and then we also need to apply timing constraints to the design. So since in analysis, we need to ensure that what are the different constraints that need to be designed, that need to be applied for the design, this is shown to you. Okay, so all those things are available in the folder. You can cross verify and check it. Now you could able to see the design is generated. Now exactly in the similar way that we have done yesterday, we can compile the design. So the switch to LED logic is compiled. Okay. So let it perform compilation. What are the informations we should ensure in this cases? We need to cross verify whether the design is compiled, and then you can able to see the RTL schematic. You could able to see the mapped post map as well as the post placement and routing, which is called as the post fitting schematic. You could able to see for the design. Now you could able to see that the design is compiling, and you could able to see that it reaches 100%. Right. Now let us go to the pin planning for this particular design. You could able to see that it has done everything. Now yesterday when we were designing a small design like AND gate, what happened was there were 2 inputs and then 1 output. We went to the pin planning, and then we opened the DE10 light user lab manual and found what is the switch SW0 and SW1 and what is LED R0, that corresponding IO standard and the location we manually fed inside. Okay. Then you could able to see that when I go to the assignments and then I say pin planner, you could able to see that these directions and locations are not available right now. Okay? So they are not available. I need to enter pins, and then I also need to enter these 10 switches. Okay. So there are chances that I may enter something wrong location. There are chances that I may provide a wrong IO standard also. How do we solve this problem? Then you say, so the solution is provided to you in the form of a TIL file. So you can go to here, view utility windows, and then you can able to see TIL console. It is already open. So now I have closed it. So now how do you open that TIL window here? Go to view utility windows and then TIL console. When you open that, you could able to see there is a TIL console here. Okay. So what you can do is you can go to this folder where the design files are there. Here you have the DE10 light pins.tcl file. You can just open that. You could able to see there are location assignment provided for all the 10 LEDs and the location assignment provided for all the 10 switches SW0 to SW9. What is this example? Is whatever switch you are changing, that corresponding LED should glow. That means you require all the 10 LEDs as well as all the 10 switches except the clock. So just to copy everything from here. Okay, and that you can paste it to your TIL console here. Okay. Here you paste it and then say enter. Now the moment you enter everything here, now we can go to the pin plan. We're able to see that all the LED values and all the switch values are already listed. You don't want to feed them one by one. So this is available for the DE10 light board. You can try it. So now you have understood how to apply the pin constraints. Similarly, we should also understand how do we apply the timing constraints. So this logic, you need to be very clear. So you can get that information is provided to you along with the Verilog code. You can create the project, you can copy paste the code, you can compile the design, and then you can perform pin planning also. Okay. Right now we have done this. Now the moment you change the code with pin planning, what happens is you could able to see that the fitter, placement and routing, assembler, timing analysis, all those things you could be able to see that it is asking us to perform once again because you have modified the pin planning. So you can use that logic from here and that can be copy pasted into the design. Okay. Right now, what we can do, we can again compile the design. So this is the advantage of the Quartus Prime skill console. Okay, the same will be helpful for us while performing the timing analysis also. So while performing the timing analysis also, you can apply the commands one by one in the tickle console and update it. Or you can create a synopsis design constraint file, which is called an SDC file, and put all the commands at one stretch in that file, save that file, and that could also be applied to the design. So there are different ways. Now this will be a shortcut for us because you don't want to enter the pins one by one, because it will take a lot of time for us, and then it is error prone also. Sometimes when you open the bank properly from the lab manual, you would have seen pin P11, but while typing you would have given pin P12, then it would be a problem for us. And then when the design gets implemented, and then while generating the programming files, you'll get a lot of errors. So then it is better to avoid that problem. It is always better to go ahead. Okay, now you could able to see that the design is generated. Now you could able to see assembler generating programming file. Then you could able to see all this flow is happening, but you could able to see the timing analyzer is still showing red. That means, have we applied any timing constraints to the design? When you say no, we have not applied. So you see that it clearly shows that the design is not fully constrained for setup requirements. Have you applied any constraints for setup requirements? When you say no, have you applied any requirements for hold? The design is not fully constrained for hold requirements. So that means the design is not constrained for setup requirements, and the design is also not constrained for hold requirements. That means we need to apply proper timing constraints for setup and hold. Only then we can go to the next step. So that's what you could able to see, that timing analyzer showing red here. All other things you could able to see that. Entire flow we could able to do that. Okay. So yesterday's pin constraints, when you see, we have applied that manually. Today, what I am trying to show you is you can copy paste that into the tickle console. Automatically, all the pin constraints would be updated, and that you could able to see here. Okay. If you have the clock pin for the design, you can add one more node where clock pin can also be added, so that you could able to see the clock frequency 50 megahertz along with the 10 switches as well as the 10 LEDs. So I will close this design, and then we let it be present for some time so that you can apply the timing constraints that are required for a pure combinational logic block. And then we can also enter into the design and try to see what are the other options available for a sequential logic block, and how do we constrain all the paths in a timing analysis design. Let us go back here. So you have a setup report as well as the hold report, which I showed you earlier. You could able to see report timing, and then either you can see the setup report or you can see the hold report. Either you can perform setup analysis or you can perform the hold analysis. Any analysis is fine for us. But then how are we going to apply those constraints? So we have seen now how to apply pin constraints. Either you can do that manually, or you have a tickle script file where you have all the pin locations and assignment already set. We need to just copy the tickle constraints and then enter into a tickle console window, which is present in the utility logic. Automatically, the tool takes care of it, and then you can compile the design and generate the programming file. But then there is a way to apply the timing constraints in the tickle console. There is a way that you can generate a tickle file, which is called as the synopsis design constraints file. Right. So after generating those things, you could be able to see multiple reports that are generated by the tool. I will show that in the demo, and then we can revisit them again in this case. Okay. All right. So different Slack reports are generated. And what is very important for that in SDC terminology is we need to know what is cell, what is pin, what is net, what is port, and what is registers. So to get into the diagrammatic principle, you could able to see what are the things that are available in the SDC netlist, which is called a synopsis design constraints netlist. You have the cell, and then you have the pin, and then you could able to see port, and then you could able to see the cell. Okay, so this is the net which is interconnecting it. So you should know cell, and then net, and then port. So when these informations are known to us, we could be able to easily identify that whether it is a pin or it is a net or it is a port or it is a cell. So based on that, we can get them. It can be get underscore cells, or it can be get underscore pins, or it can be get underscore nets, or it can be get underscore ports. Okay, right. So let us start with the understanding of how do we create a clock, because while going through the exercise, we could able to see that there was an example where the clock frequency was specified as 20 nanoseconds. And then we have seen that the design is not meeting with 20 nanoseconds because there was a violation of 1 nanosecond. So we have to increase that to 21. Automatically, the frequency is getting affected for that. So how do we create a clock for a design? So now you could able to see that how do we create a virtual clock or a base clock? That is, what is the way to create a clock in the design, and what is the command that need to be applied for generating the clock. Let us see that. Create underscore clock. You could able to see that create underscore clock is the command name, and then name of the clock. You could able to swap them also, no issues. Create clock. If a name of the clock, then hyphen period of the clock. So create underscore clock, hyphen name of the clock. You can give any name, hyphen period of the clock. So 20 nanoseconds is the period. Get ports. What is the name of the clock you have given in the RTL? So that name you can provide it here. So now you could able to see when it is a 20 nanoseconds clock, it starts at 0, falls at 10, then again it rises at 0. So that means 20. So you could able to see that, which is a clock period of 20 nanoseconds. But then there are chances that we don't have the 50% duty cycle. If there is a change, then we have to come up with one more extension called as hyphen waveform. When you say hyphen waveform, what happens is create underscore clock hyphen period, you say period, but hyphen waveform, you should say 0.0. That means it rises at 2, and 8.0, that means it falls at 8. Okay, so now you could able to see that this provides you the period. Now this is the base logic for us. So either you can use the hyphen waveform syntax, or you can use the create clock logic. So create clock is easier because you will have the 50% duty cycle where you can directly write the 20 nanoseconds clock. What would be there in the GUI? You could able to see create clock, and then you can provide the period, and then you can see rising, and then falling, get ports clock, and this is the command that is automatically coming. So when you're doing that for the first time, the tool will generate all the SDC commands here, so that you can copy paste and then keep them, and that could be created as a TCL file which you can source that, so that you can reuse that commands for any kind of design. That is the basic advantage. So when you are doing that for the first time, it is recommended to do that in the GUI, and it will generate some set of commands for us. We can copy all the commands which is generated by the tool, and that commands can be copy pasted, and then we can create a TCL file, and that TCL file can be sourced so that we can reuse them. So you can create the clock for the design. So create a clock using GUI. So this is the logic here. Okay, right. So now what we also need to understand is how are we going to understand that the design is not having any violations, and how do we generate a clock for a specific design? I have a design and I need to generate a clock for that design. How do we do that? That we will see in detail right now. Let us open one example project. I'll just, as of now, just hold this for some time. I will close this project, which is the project new timing switch to LED. Let us open a project which we have seen simulation yesterday for a small counter design. So we will open that design now. I say counter simulation. Let us open that example here. And say counter.qpf, which is called as the Quartus project file. You open it. Right. So now you have the counter design. You could able to see that you have E down to 0 Q, It shows always a cross edge of clock or negate of reset. If reset Q is equal to 0, else Q equal to Q plus 1 is there. Right. So it is a 4-bit up counter for us. So let us compile the design right now. Exactly the similar way what we have done. Please understand the informations are available for us. So you could able to see the total number of registers, it shows 4. Total number of logic elements, it shows 4. So you can able to extend that from the filter and see what are the options that are available. Yesterday I showed you how you can see the RTL schematic as well as the post mapped as well as the post fitting, the placement and routing also. Right. So now you could able to see that the design is able to generate the programming files, and then it shows the timing analysis. Now you could able to see it shows red. That means we need to apply timing constraints to the design. How do we do that? So listen carefully. Go to the tools here, and then you could able to see there is a timing analyzer. The tools and then say timing analyzer. We can click that. So now it opens the window for us where we need to select a timing corner. Okay, that means you need to provide what is the process, voltage and temperature in which you wanted to check this design, where the design need to be subjected with that. So for that, the moment you open this, you will be having 3 important informations here for the netlist setup. One is called the create timing netlist, read SDC file, and update the timing netlist. So you can just say create timing netlist. Now you could able to see that we need to provide the clock for this particular design. How are we going to apply the clock for this design? That we are going to see right now. So you could able to see on the top, file, new, view, netlist, constraints, reports, script, tools, window, everything is there. Now, if you click the constraints here, you could able to see there are a lot of constraints that are available here. Okay. First one is called as the create clock design, which we are going to create the clock now. So I say constraints and then say create clock. You click it here. And then what is the name of the clock that is used in this design that we should provide? So I say CLK. What is the name of the clock? And what is the period is 10 nanoseconds. That is my period. So see the GUI window, which I showed you during the presentation. Exactly in the similar way, you have create clock. What is the name of the clock? I have provided clock CLK, and then period I have given 10 nanoseconds. And then what you are supposed to do is you have to specify the target. So you could able to see there are 3 dots here. Okay, just expand that. And you are asking the tool to list it. What are the clocks that are available? So for example, I say list. When I say, automatically I could able to see the clock here. So when I say list, it shows 6 matches found. But these 4 are outputs and this reset is an input. And then you have a clock. So now select this clock and bring that to this side. Okay, automatically the tool generates SDC command, get underscore ports, and then clock. Now you can say OK. Now you could able to see it generates an SDC command for us. Create underscore clock, hyphen name of the clock, hyphen period of the clock, and then it shows get ports clock. Now you can copy this command, and this command can be reused. Or you wanted to change this period to 12 or 14 or 15, you can just keep as it is. You don't want to come to the GUI and again change it. Okay. Now the moment you gave create clock and then you gave the name of the clock and then you allowed the period and then you applied the targets. Now we say run. So now you could able to see that it shows create underscore clock, hyphen name of the clock, hyphen period of the clock, get outputs clock. So this is the syntax which I showed you in the timing analyzer slide. So what is the way to create the clock? When you say, you can directly apply that in the tickle console. So you can able to see there is a tickle window for you. Directly you can apply the command here. Now I wanted to do that in GUI. When you say yes, we can. Now we have created the clock. It shows create clock, if a name of the clock, hyphen period, then period of the clock, and then say get ports, and then clock it is provided. Now what we are supposed to do is, since we have created the clock, we can ask the tool to report that clock whether it is generated properly or not. So what we are supposed to do here, you could able to see there is a Slack tab where you can see the setup summary as well as the hold summary that you can cross verify and check. And you could able to see that report clocks. You could able to see that. Now you could able to see report clocks. When you click, it shows that the clock is generated and the period is 10 nanoseconds, which is 100 megahertz. And 0 it will rise, and 5 it will fall, and then again 10 it will rise. So that is the frequency we have provided. So we didn't use hyphen waveform, and then we didn't do non 50% duty cycle. So it automatically takes that the moment you provide it. So the moment we gave report underscore clocks, you could able to see that what is the clock that is generated by the design. That means what constraints you have applied. For that specific constraints, you could able to see that. Now, what is the another information we should see is, you have a set of paths in the design, but whether the design is having any violation when you apply 10 nanoseconds, that we have to see. So now you could able to see, while going through the schematic of this design, you would be having multiple paths that you can see. For example, you go to the netlist viewers, then you can go to the post mapping. You could able to see that it has register to register path. That means you have input to reg, you have register to register, reg to reg, then you have register to register, that is again reg to reg, again reg to reg, register to register, and then you have reg to output port. You can able to see there are multiple paths in the design. Now in this, which is the critical path, which path takes the longest delay, that becomes a critical. That means the constraint what we are applying right now is for the clock constraints. The clock constraints what we have applied is applicable here. We have given 10 nanoseconds that it is going to take from register to register. Whether the design is having any violations or not, that we need to check. For that, we require two parameters. One is called as the required time and the arrival time. And what slack we are going to see is called as the setup slack. So now we don't want to do the pencil and paper exercise here. Automatically, the tool would have found out what is the data required time and what is the data arrival time. And then it will also show you whether the setup slack is a positive number or a negative number. How do we ensure that it is correct? So we can go back to the timing analyzer window here. And then you can able to see there is a tab called report timing. That you can check that, or you can see setup summary. It is easy to directly go to report time. So you could able to see there is a custom report. You can double click that report timing. Then you could able to see that is for setup, for hold, for recovery, as well as for removal. Now we are just saying setup paths. Report number of paths we require 1. You wanted more, you can enable that there. And what is the command is the report timing command. Now you could able to see the entire tickle command. Whatever you enable from here, that will be automatically added in this place. Say report. Now you could able to see that the setup slack is 8.967. It shows that means from the statistics you could able to see that in the path summary what is the arrival time and what is the required. What is the data required time and what is the data arrival time the tool has calculated. You can get that information by entering into the data path, where what is the data arrival path. It provides the details from where it starts, that information is explained. And then the data required path, because our requirement time is 10 nanoseconds. All these informations are provided. along with the waveform. You could be able to analyze the waveform, which is the start and which is the clock delay, which is the data path delay, then which is the slack. So it has found out. You can see the green bar. This explains you about slack well. Now you could able to see the path summary specifies that from where it starts one register and where it ends, that is the source register to the destination register. What is the launch clock and latch clock? Both clocks are same. Okay, because in our case, the launch flip-flop and the capturing flip-flop are using the same clock. But that may not be the case when it is a multiple clock domain, which you will discuss in the next session. Okay, you will have more than one clock. But in this case, we are trying to understand that the launch clock and the capture clock will be utilizing the same clock. So the data arrival time is provided to you and the data required time is provided to you. Now it is going to subtract. What is the formula? We are aware that it is a data required time minus data arrival time. So it shows the required time minus arrival time. And then it shows the positive number, which is 8.967. Similarly, we also need to check for the hold check. We have just checked only for the setup logic. We have to also check for the hold logic, whether the design is having any problem with the hold violations. Okay, so what is the formula? We have already seen that it is arrival time minus required time. But in this specific scenario, how are we going to see that in the GUI? Okay, you could able to see here, found one set of paths, 0 violated, nothing is violated. Worst slack is 8.967, it shows. Similarly, you can click here report timing. Instead of setup, you can select hold path here. And then you can say report timing. You do hold path and then you can say report timing. Automatically, you could able to see that the data arrival time is this and data required time is this. It is 80 minus RT. So 3.854 minus 3.530, which shows 0.324. So you could able to see that the setup slack is also positive and the hold slack is also positive. But what we should also understand in this case is, have we applied the constraint for all the paths? Then we say no. We have applied the constraint only for the register to register path, because it starts from a register and then it ends at a register. So we have given the clock information for a register to register paths. But in the first slide, when we started the timing analysis, you could able to see that there are 3 paths that were available. One is for the input to reg path. The other one is register to register path. And then the third one is register to output path. But what we have applied constraints so far is only for the register to register path. So have we constrained all the paths in the design? When we say no, the design is not properly constrained. But what constraint we have applied so far is for the register to register path, which we have applied the clock constraints. How do we know that whether all the paths are constrained or not? Or how I need to understand that which are the unconstrained paths that are available in my design? That also could be seen. How do we approach that thought process? You could able to see that there is a command called report unconstrained paths, so that you could able to see that. When you click report unconstrained paths from here, it shows that illegal clocks 0 and unconstrained clocks also 0. No problem. There is no problem in the clock constraints that you have applied correctly. But what are the problems we have? Unconstrained input ports. That means for the input port, that is input to reg, have we applied any constraints? When we say no. And then unconstrained output ports. That means for the register to output. For reg to output also, we have not applied any constraints. So you have applied constraints for the clock, that is register to register. There is no constraint applied for the input to reg path, and there is no constraint applied for the register to output, reg to output. So input to reg as well as reg to output path we have to constrain. So only then you can see that the design is 100% constrained. So when we applied the pin constraints for that design, we have seen that all the pins that are required, we applied the constraints effectively. That means we didn't miss any LED, any switch. All the LEDs and all the switches, whichever required for our example, we have programmed it. Exactly in the similar case, all the timing paths should be constrained. We should not miss any path. What happens when you miss that path and that path is not meeting timing? And that is the critical path. We will be in trouble then. The design will have issues. So it is always recommended to ensure that we are not missing any timing constraints in the design. So what we also need to understand in the later section is how are we going to apply timing constraints for the input to reg path as well as for reg to output path. So what are the constraints and those commands, how it will help us to perform the task. Again, we have to understand that we have to be very clear that that need to be done for setup as well as for hold. Therefore, you will have two values. One value is called as the maximum value that is useful for setup analysis, and the other one is called as the minimum value, which is used for hold analysis. So we have to come up with two sets of values. One is for the setup and the other one is for the hold, and then we have to constrain it. So that is the base thought process. Now you would have understood that yesterday's example we have just taken, and in the similar example, the design is compiled, but we are trying to enter into the timing analysis, and then you entered into the constraints tab, and then we applied the constraints one by one here. One is the create clock, and what are the other constraints that are left out and that we need to apply? I will list out right now. The second one is called as the set input delay. This is for the input to reg paths. And the third one is called as set output delay, which is for the reg to output paths. And then you have a set max delay. This is for a pure combinational path. Set max delay, that's a maximum value. And then set minimum delay, that is the minimum value. Because we also have a pure combinational design where there is no register at all. Then what is the constraint that will be applied for a pure combinational logic path? When you say we need to apply set max delay and set min delay. And then in the next section, we will discuss about the set false path and then multi-cycle path. So that means we all call this as timing exceptions. That means you have a false path in the design. What is that? We will discuss in detail. And then you may also have a multi-cycle path in the design, because STA assumes that from the launch flip-flop to the capture flip-flop, it should take exactly only one clock cycle. But there are situations in STA where you may require more than one clock cycle to propagate the data from one flip-flop to another flip-flop. So in that particular case, we cannot complete the process within one clock cycle. So we call those paths as multi-cycle paths. So multi-cycle paths are paths which takes more than one clock cycle to propagate the data from one flip-flop to another flip-flop. So we call those as timing exceptions, because that is not going to happen at all times. And you need to apply the proper timing constraints for those paths. How do we apply that? That also we will see in the today's discussion. So we will discuss more on create clock that we have seen now, set input delay, set output delay, set false path, set multi-cycle path, set max delay, and set min delay. So all these commands, we will try to sort it out and then do them one by one. Let us get into the session here. So I have shown you how to apply the clock constraints. After applying the clock constraints, what is the impact on the setup? What is the impact on the hold? I showed you with an example. And then what is also very critically important for us is, have we applied the constraints, the proper timing constraints? When we say yes, but have we applied for all the paths means no. That means when you say report unconstrained paths, the tool is trying to show that we have not applied. Now, what is the base thought process? You could be able to see that here. Illegal clocks, it showed 0. Exactly the similar way what I showed you in the lab demo. Unconstrained clocks, you could be able to see 0. Unconstrained input ports, you could be able to see 33. Unconstrained port paths, you could be able to see 34. And then unconstrained output ports, it shows 32. And unconstrained port paths, it shows 32. That means you have applied constraints only for the register to register path, but you have not applied constraints for the input reg path as well as for reg to output path. Exactly the same information was shown when we have gone through the example what I showed you, because it has only 4 registers, so it showed only the 4 paths. But then the design is quite complex, it can show you multiple paths for you. Right, so that information we have to see what is the name of the clock. Report clocks I clicked and showed you what is the command. If you don't want to see that in GUI, you can also apply report underscore clocks in the tickle console. You could be able to see what are the clocks in the design. Now we are understanding how we are going to apply timing constraints for a pure combinational path. So that is very, very critical for that. Now why it is important for us? Because I have a design which is having the input port. It starts from an input port, but flows through the combo logic and ends at an output port. Let us take the example of a switch to LED, or let us take the example of an AND gate, which we have done yesterday. What is available? You have A, B, and then Y is there. So where is the register there? Nothing is there. It starts from an input port, flows through the combo logic, and ends at the output port. So when you are going to apply timing constraints for a pure combinational logic design, then you can try to apply set max delay and set min delay. That is the command that has been provided. So set max delay is the maximum delay. That means you are providing a worst case delay from your side. And the set min delay, that is equivalent to your fastest path. So what is the worst delay you are expecting? And what is the best delay you are expecting? How do we constrain this? When you say all the paths from in output need to be constrained, that means you can use a shortcut that you can use all underscore inputs and all underscore outputs. That means all the inputs can be constrained and all the outputs can also be constrained at a combinational interface. So this is quite required for us, because we need to take a design which is a pure combinational logic design. How are we going to constrain that logic? That information should be known to us. It can be any specific delay, but then it is always recommended to identify what is the critical path and then you can apply. Or you can provide some delay and check based on that what is the value it is taken by the tool. Is it showing negative or positive? We can experiment also. There is nothing wrong in experimenting that thought process. Let us go back here. The design which we have right now. I will close this counter project at this junction. We will open it again to apply the timing constraints for input to reg and reg to output path. Let us open the switch to LED portion which we have seen earlier. Now we'll open this design and then we can compile the design once again. Okay. Right. So while compiling the design, it is very critical and important that the design is already having the pin constraints that we have seen. But then we are also going to see, are there any timing constraints required for that design? And then whether everything is fine. Because in this specific logic, there is no clock required. When the design is not having any clocks, then how are we going to constrain that particular design? That's what I showed you. What is the command that need to be applied? So command what we need to use is called set max delay and set min delay. This is for a pure combinational logic block from the input to the output. Okay. You could able to see that design is not fully constrained for set of requirements and design is not fully constrained for hold requirements, it shows. Right. So now what you can do is you can go to the tools and then go to the timing analyzer and say create timing netlist. You can select any timing corner that are required. Either you can select slow or fast, whatever you want. Different timing models are there. That information is provided in the lab manual. You can have a look at it. Now you could able to see that it can generate a constraint. I say here set maximum delay. Let's set max delay. I have provided here. Somewhere you say it can be from all inputs. So I just say here all underscore inputs, because it's a pure combinational path. You wanted, you know, through, that means via what, then we can provide that. If you are not knowing that, it is better to directly write all underscore inputs to all underscore outputs. And then I provide a delay value here. For example, 8 nanoseconds I am providing. So this is just a random value I have just picked up. Okay. to understand the flow of timing analysis. Just say run. Now you could able to see that set max delay hyphen from all inputs to all outputs, it showed 8 nanoseconds it has taken. Similarly, I need to again go back to the constraints and say set minimum delay. So when I say set minimum delay, now again I can say from and say all underscore inputs. That means I need to provide the fastest information to all underscore outputs. From all inputs to all outputs, I should provide some minimum number. For example, I say 5 nanoseconds. I just say run. So set max delay hyphen from all inputs to all outputs 8. Set min delay from all inputs to all outputs 5 I have provided. Is there any impact that we can see that? First, we can see report clocks. Is there any clock in the design? You could able to see that no clocks to report. Okay. Is there any information in the timing that we can see? Report timing is set up. That is your maximum delay. Say report timing. You could able to see that the data arrival time, it shows 7.796 and the data required time what we provided is 8. So you could able to see that, okay, 0.204, right? So what is the statistics? I want to see that. Yes, you can see that. What is the data path delay is 7.796 and how we are getting this delay is explained here. The cumulative addition of all the values you could able to see that provides you 7.796. You can see that in the data path, what is the data arrival value and what is the data required value that is specified here. And then you could also able to analyze the waveform, what we provided and what is the time taken for the circuit to reach that output port. That information we have seen. You could also see here, what is the slack value positive, from where it starts, SW of 5. This is the input switch. And then where it goes, LED 5. So from the switch 5 to LED 5, we told that the maximum can be 8. Okay, and the delay what is taken is 7.796. So 8 minus 7.796, it shows it is a positive number. Similarly, you can check for hold. So report timing. Instead of setup, you select hold here, and then we can say report timing. Then you could able to see that the data arrival time is 6.983 and the data required time is 5 nanoseconds. The formula is AT minus 30, that means arrival time minus required time. You could able to see the slack is a positive number. So we have seen now how to apply timing constraints for a pure combinational logic path also. So when it is a pure combinational logic path, what is very important for us, we are going to provide a set max delay and a set minimum delay component. By providing that set max delay and set minimum delay component, you could be able to see that the design is able to meet timing or not. If not, if it is showing violations, we have to go back to the tool and cross verify why there is a larger combo delay that we can check. Why between the input to the output port, if there is a larger combo delay, we can check that. You can see the number of logic levels in the statistics. You can able to see the number of logic levels is only 1. So only 1 logic level is there. But if there are multiple logic levels, for example, I have 5 or 6 logic levels, it is always better to reduce the logic levels. When the number of logic levels are lesser, then it is easy for us to proceed further. Right? There are different techniques that is available in timing analysis where we can perform, which is, for example, pipelining. You can do. We can reduce the number of logic levels. We can insert registers into the data path in order that you can reduce the data path delay. But then you should also see that there is an expense of flip-flops that is used in the design. That also we have to cross-verify. There are multiple components that are taken into picture. And you also need to know that how do we apply different timing closure techniques to achieve that. This is the example I applied. You could able to see set max delay and set min delay. I provided the values. If you wanted to apply specifically, also you can apply. I have applied directly all inputs to all outputs. If you are applying only for one particular, also you can apply. This is the D in. This is the input register. That means it's an input port. Directly it goes to the output port. So for all the things, you will have the commands ready. You can use these commands to get into the next logic. You can apply specifically like this also. One by one you wanted to apply, yes, you can apply. You wanted to apply all inputs to all outputs, yes, you can apply. That is also possible. Okay, right. So before entering into the constraining the synchronous input ports, if there are any questions, I can answer one or two questions and then we can take a break. And then I will show the demo of the constraining the design, and then we can enter into the false path and multi-cycle paths. Are there any questions? Please let me know. Or else we can take a break for 5 minutes and then again we can resume and start. Are there any questions which I can take up now? Are there any questions in the chat? Shall I proceed? Are you able to hear me?
Hi, Paddy. Yes, you are audible.
Okay.
There is one question in the chat box.
Okay.
How can we calculate the min delay and max delay for the given data path?
Okay. Right. See, the idea is like we are going to apply the constraints right now for the values, right? So we have to identify which is the critical path first. That means we can understand that the tool is going to provide you what is the critical path of the design. And you know that what is the operating frequency or design has to work, right? We are going to apply the timing constraints. In the first exercise, when you have gone through that, you would have seen that the design is not meeting timing because we wanted the design to work at 50 megahertz, which was impossible. So first we are applying the timing constraints and check whether the design is meeting with that timing or not. That's what I'm going to show in the demo during the timing analysis. So first our requirement is important. We have our own requirement, and then why the design is not meeting that requirement we have to see. And then step by step we have to understand that what is the issue and how are we going to fix it. Okay. Especially for the input to reg path and then for reg to output path, the information would be given by the PCB designer. That means during the interface, what the delays that would be provided by them. Based on the T min and T max that is provided in the data sheet, we have to fix our requirement. Okay, but in this specific scenario, since our design, I wanted my design to work at 100 megahertz. I checked whether the design is working at 100 megahertz or not, or it is having any issues. Okay, so if the requirement is the design is expected to work at 100 megahertz, you have to feed the clock at 10 nanoseconds and cross verify with that whether all the paths are meeting timing or not. Okay, most of the values would be given to you by the tool, but then you have to cross verify and check whether all the paths are meeting that requirement. Right. If there are no questions, shall I continue then?
So let me see just a minute.
Yeah.
I could see a few questions. How to calculate the slack, stop, and hold for n number of registers? Could you please repeat?
Okay. So for n number of registers, right? There was for logically, if you see here, it is going to take for only one path. When I say report timing, it is going to take it for a single path. Number of paths is only one by default. Okay. But if you wanted to make it for more number of paths, you can just say how many number of paths you want. You can just say report timing. The tool will try to show for all the paths. By default, the report timing command is going to show you a single path. That means which is the critical path, which is having the highest value that it is going to show you. But then I wanted to list down all the paths and then I wanted to see the delay in all the paths. Yes, you can definitely do it. Either you can apply the command report timing and then -max paths 10 where you can get the worst paths also. Or you can do that in the GUI where I have changed 1 to number of paths. How many number of paths are available that you can able to see. But then which path was the critical path? Okay, only that was listed first in the earlier case. All other paths other than that, those paths are having the least delay.
One more question is, can we integrate Simulink with Quartus for communication applications similar to Xilinx system generator and check the design in real time?
We have that session on Thursday. We call that as Intel DSP Builder. Okay, DSP Builder with Intel FPGAs, where we will integrate MATLAB Simulink, and then we will see the model sim simulation, and then we will integrate Quartus, and then take the design into the Quartus, generate the RTL, and then we can check for the RTL schematic, and then we can also check for timing. We will show the entire flow on Thursday.
One more query that I could see is, if we are implementing an algorithm, how to set constraints and calculate maximum frequency that algorithm works?
Correct. See, the idea is like, again, you have to find out. See, without applying the timing constraints, when you are going to see report timing of any particular design, what it is going to show you is the critical path, right? It is going to just show you a number, right? I am not applying any constraints to the design. That means I am going to see which is the critical path. When I say report underscore timing, from all registers to all registers, from reg to reg, I am going to get a number. Because the design is not constrained, I am going to get only the arrival time. Okay. So the one, in this case, for example, if you see which is the critical path, when you say 7.796 nanoseconds is the critical path. But on seeing this only, you could able to see that I need to apply 8 nanoseconds. That means this is deciding the operating frequency. So you have to identify which is the critical path in the design that decides the operating frequency of that particular logic. Or if you have a specific requirement, you can apply those constraints to the design and then see why those paths are failing. And you can take separate measures or you can take specific measures for those particular paths in order that they can take your requirement also. Sometimes that path is a critical path, but then there are 10 logic levels in that path. Because of that, it is not meeting timing. You can take a decision that either you can go back to the RTL and modify the code, or you can apply the pipelining stages and other things, like you can apply that, or you can think of retiming, whatever may be the different techniques which you can think over and try to optimize the design.
Sir, we are providing only the max and min delay. So how is this able to calculate the data delay on its own?
The data delay is taken from the library, right? So the data delay is nothing but the propagation delay, right? This is the T clock to Q, the setup time, the hold time, all those informations, your combinational delay is available, right? So the tool takes care of it. What you need to worry about is how are you going to reduce the number of logic levels between two successive registers? That's what we should worry about. Because if the number of logic levels between two registers are very less, then you can make the design to operate at a higher frequency. For example, I have one register and then to another register, I have 10 gates, 10 AND gates are there. I have to cross 10 logic levels to reach another registers. Every gate will have a TPD max and TPD minimum. And then if I need to cross 10 AND gates, for example, I have one. So each gate is having 1 nanosecond. So I will get 10 nanoseconds to reach it. So the data path delay itself is 10 nanoseconds. How can I make my design to work at 100 megahertz, right? It is very challenging for me. So while developing the Verilog code itself or VHDL code itself, you should code in such a way that between two successive registers, right, the number of logic levels should be lesser. When we take care of that while coding, then we don't want to worry about it during timing analysis. Okay, all other delays are given by the tool only. It is taking the statistics calculation.
Just a few, let me just check if there are. How can real-time signal processing be simulated?
Your question is on the simulation or your question is on the timing?
The question reads, how can real-time signal processing be simulated? I request Shreya ma'am to kindly reply what exactly she wants. Also, a question is the timing analysis examination to performed very first to avoid unnecessary delays? We oversee the delays. What are drawbacks?
It is always better to apply timing constraints at the synthesis stage, right? For example, you know that these are the requirements, right? If you are aware of what are the requirements of that design, it is always better to apply that prior at the synthesis stage and then check, okay, whether that is taken into account. Okay? Because when you take a AD design, you will be getting the details that what is the maximum operating frequency you want that design to operate. Is that applicable or not? That we can check. One is that. The second thing is you apply the constraints and then you could be able to see with these constraints only the design is not having any violations. So from that, like the paper and pencil work, when we need to apply 50 megahertz, the design is not working because the setup slack is negative. That means even if you try to make it, your design will get violated. So in that case, we have to increase our clock frequency. That means you have to increase your clock period, which affects the frequency. In some cases, there should always a compromise between what we wanted and what we are getting. Okay, so we cannot say that, okay, our design will definitely be timing with the constraints. There are chances that it may not meet, but there are different techniques that are available in the tool, which will help you to meet your requirements. That is possible.
How do we actually estimate the max-min delay? It would depend on FPGA LE properties.
The max and the set max delay and set min delay, what I have applied for the combinational logic block is based on the critical path delay, because you could able to see the critical path delay was 7.796. So I cannot give lesser than that. I can give 7.8. That's all. But what is the problem is if anything changes, the process, the voltage or temperature changes, or you are subjecting this to something, what happens is when you have a slack value, which is a better positive value, there are chances that the design may not go into violation. So I can appropriately provide 7.8 nanoseconds because my delay is 7.796 and requirement I can give 7.8. But the problem is if the slack is very near to zero, if the value is very near to zero, there are chances that it will go to negative. Therefore, there should always be a tolerance where we are providing a positive value. That's what when we give 7.796, we give 8 or 8.5 as the requirement. So this will provide you a window for us that what kind of operating frequency the design can operate.
Thanks, Shreya ma'am has repeated the question. Using this software, can real-time signal processing be done or any other method needs to be used?
Yes, I would like to answer this question. Yeah, sure. Right. Thanks for asking this question. Yeah, using this software, which is timing analyzer, cannot be.
Ritesh sir, your voice is a little feeble. Can you please check back your audio?
Yes, give me. Is this better? Is it better?
Yeah, better.
All right, perfect. Sure. So this is a timing analyzer tool, which is a static timing analysis. Basically, your code is generally analyzed statically with the timing models of all the parameters which are there on the FPGA resources. Like let's say the clock which is used, right? The register which is used in the FPGA. It has all those clock to queue delays and all that modeled, and they're used. Those pre-modeled timing data are used internally by the tool, right? And that is where you can simulate those timing parameters, and you can see whether your signals are meeting the timings or not. But however, if you want to check, if you want to really simulate the real-time data and see if if it's kind of passing the timings, definitely it's tough to do, because that's where static timing analysis comes, right? It tells based on the data which it has and the constraints which you give, it tells whether it could meet, or what are the slacks, and um, uh, how much of the window you have to meet the timing. That's one. And there is another tool called signal tap analyzer. I think that you would be interested in, because a signal tap analyzer provides you an access to the waveforms of this real-time signals in the FPGA. So you can see how the data is processing, like what changes are happening on your data bus or in your control signals, like whether it's going high or low. Uh, that can be easily done by using signal tap analyzer. And I think we will be discussing that in one of our sessions later. I think in day 9 or day 10, we'll be discussing that. All right. Back to you, Padmanabhan. Thanks.
Thanks, Ritesh.
Sir, are we done?
No, I'm just telling that can we take a break for 5 minutes and then
sure,
I will
sure,
start
sure.
the demo. Yeah.
Yeah, sure,
And,
sir. We can take a break of 10 minutes. No problem.
Yeah.
sure. And I'll be responding on the chat or Q&A section. So
Yeah,
if
sure.
any
So
questions
the
you have.
next session will be taken by you, Ritesh, sir?
No,
No,
actually, I will continue another half an hour. Then Bhaskar will continue the session.
Oh, okay. So, okay, fine. So let's take a 10 minutes break. We will meet back at 11:50 and we will start the next session. Thank you, everyone.
Okay, welcome back. I'll start the session now. So you would be getting the timing lab manual where you could be audible.
Yes, we can hear you.
You could able to see there is a timing lab manual in which I will show you what is the specific lab. You're going to restore the project. The Quartus archive file would be given to you, like what has been shared with you. Okay, similar kind of examples are provided. In the first lab, what we are going to do is we are going to analyze the timing analyzer files. You are going to perform the multiplication and addition, and you are going to add two numbers and then multiply by another number. We are going to perform the fitter operation, and then we are going to give the RTL schematic of this particular design, and then we are going to perform timing analysis for this design. We are going to apply some constraints. That means we are going to apply the clock constraints for that design, and then check whether the design is able to meet timing or not. That's what we are going to update. We're going to provide some clock of 12.5 nanoseconds. And then once we give that value, what is happening to the design, we will see. And then what is the violation and what is the value which we need to provide, that we will see in detail for this specific design. All the informations are given step by step for you so that you can go through this and why we are getting violations and how are we going to solve that problem, and you can see all the things. I have shown you with one example, but then I will open the same example what is given to you as lab exercise, and then we can identify that what is the specific logic in analyzing this clocking report. So you could able to see the design files here. The first one is called as the timing analyzer.qar file. The other one is the multi-cycle path.qar file. Both files are available here. You can copy that. Then you can create a new directory or new folder. I just say just the timing. I say 1, and inside that I paste this file, which is the timing analyzer.qar file. I open the Quartus. I close this project. Now I can go to open project from here, and then I can go to my folder, which is timing 1. And inside that, you could able to see the timing analyzer.qar file is available. Just click that and save open. Now it is asking you to unarchive. Just say, then continue. Now you can analyze the design. You could able to see this is a Verilog code where you have local parameter input width is 128 and the sum width is 258 because we are going to add two numbers and then multiply. So you could able to see that reg sum is equal to reg A plus reg B multiplied by reg C, and whatever output you are getting, that you are assigning that to a sum, which is a wire. You could able to see that sum width is 258 minus 1. Okay, which is 257 down to 0, which is 258 bit. So that you are going to assign it to a sum, which is an output. Right, now let us perform the compilation, and then we can go to the timing analyzer window and we can apply the clock and see what is the value. So please follow the steps what is provided in the lab manual. That will be helpful for you to understand the timing closure better. Anyway, I will show the steps here. All the examples, that means whatever commands are there, I will show you. What is the way to see setup summary and how do you see the hold summary. And then how do we see the report timing example. All those things I will show you one by one. And why the design is violating also we will see. So you could able to see the total number of logic elements, 928, because yesterday's design, if you see here, you got total number of logic elements, you got 4 or 5, and total number of registers we got in the earlier design 4. But in this design, you could able to see the total number of registers, it's showing 514. And total number of logic elements, you could able to see it is increasing now 797. Okay, so now you could able to see that it shows 100%. Now the compilation is done. Now we can go to the timing analyzer tab. So go to tools and then timing analyzer. And say create timing netlist. Now you could able to see that we are going to create the clock for this design. So as per the lab manual, we have to create a clock of 12.5 nanoseconds. You can specify here 12.5 nanoseconds. Then what is the name of the clock? You can say here CLOCK, that is the name of the clock. Then targets, you can click here and then you can list here. So all informations can be available, or either you wanted only the clock, you can just say here clock. You can match that clock and then you can bring that here, get ports and then clock. So I have given here clock and then period 12.5 nanoseconds and the get ports clock we have provided and then say run. Right. The moment you created that, you can go and then check the report clocks here. As I explained you could able to see the report clocks here, which is 12.5 nanoseconds. And then we are going to check whether this 12.5 nanoseconds is sufficient because what is the data path delay, we should see that. For that you should go to report timing. And then for setup also we have to see, and for hold also we have to see. So we can see here report timing. So we can see for the setup paths. Okay. I say setup and then say report timing. You could able to see that the requirement time is data delay is 22.384. Then we have given the clock requirement as 12.5 nanoseconds. So you could able to see that the data arrival time is 26 nanoseconds, right? And you could able to see that the data required time is 16. So we have provided a requirement of 12.5 nanoseconds, but then it is violating. You could able to see minus 9.504, it is violating. Okay, so you can able to see that the path what we have applied, the clock what we have applied, the requirement what we have provided is not sufficient because the data path delay is too high. So you can go to the statistics and then you can able to see what is the data path delay because it is 22.384 that you could able to see that. And then you could also able to see that what is the specific delay for the arrival time as well as for the required time. So you could able to see that information. And then you could able to see the number of logic levels 5. In the earlier examples, if you see the number of logic levels, the number of logic levels were less. Okay, but then you could able to see the number of logic levels are more here because between one register to another register, you have 5 logic levels it has to cross and go. Because of crossing that 5 logic levels, it is not able to be timing. So that's what I told you when we were writing the vanilla code. It is very important and critical that between 2 registers, you should have only the lesser number of logic levels. Right now, you could able to see that the design is showing violation. You can go to the lab manual. You could able to see the same. It shows here minus 9.524, and then you could able to see what we have provided is 12.5 nanoseconds, and then what is the data path delay it shows is 22.384. Since we have enabled only one path here, it is showing one path, but I enabled all the paths. That means I gave 10. That's what I could able to see everything here. Otherwise, in the lab manual, it is showing only the first path, which is 22.384, which is the data path delay. So now it shows that found 10 set of paths, all 10 violated, and the worst slack is minus 9.504. You could able to see that which is the worst slack is minus 9.504. All other slacks are lesser than that. So we are understanding which is the worst slack in this design. So what is very important lesson we have to understand is while providing the requirement, we should always ensure that what is the data path delay that is taken by the design. So which is the worst case delay that we have to take into account. And that worst case delay is because of the poor coding style. We have to follow the recommended coding practices and we ensure that between 2 registers, we should always have the lesser number of logic levels. Okay, now what we can also do is you can apply timing constraints to the other paths. You could able to see that the data arrival path snapshot is taken, and then you could able to see how do we apply the clock constraints. Now the design is not meeting timing. I need to edit the clock constraints here. So if I need to edit the clock constraints, can I modify that again? When you say yes, you can, because now you are aware that 22.384 is the maximum delay. So you have to give the clock period of at least 23 or 24. Can I modify it once again when you say yes, we can. So what we can do right now, you can go to reports or constraints and go to create clock. And instead of this, you can just say, for example, 23 nanoseconds and say name of the clock is clock, you can provide. And then you can go here and then filter that clock from here, from the list. And then select that clock and then I say OK. Now when I run it, now instead of this 12.5, I have changed this to 23 nanoseconds. Now I can modify the clock, and now you could able to see that the design is showing 23. Therefore, we can able to see 43.48 megahertz. But then what happens to the timing? We could able to see report timing. We could able to see report timing and then take the setup and say report timing. Now you could able to see, since we have given the requirement as 23 nanoseconds and the data path delay is 22.384, you could able to see the slack is positive, 0.9696 is there. So you could able to see how do we edit that and modify, that is one. Otherwise, you can overwrite that. Earlier, we have provided some values. Since the design is not meeting timing, we should do it. But this is not the right way of changing everything, right? It is always better to develop the Verilog code in such a way that the number of logic levels between two successive registers should always be lesser. That is the proper way of applying the logic right now. Let us understand how do we constrain the delay here for the inputs. Set input delay and set output delay. So set input delay is for the inputs, which is for the max option for the setup, and set input delay minimum is for the hold. For example, you could able to see that the design is, this is your register, and then we call this as input to reg path. Even though it is input reg path, it comes from what? There is an external device. From the external device, it reaches the FPGA port. So therefore, we consider this also, this T clock to Q plus this trace delay. Also, we are considering that from the external device. So this delay we are going to provide. So if this delay is available from the data sheet, we can provide that value. And based on that, you should constrain the input. So otherwise, the input reg path, if you directly take, is not properly constrained. You are not completing the constraint. It's not a complete static STA path. In order to complete the STA path, the input to reg path, we have to assume that there is a register which is outside, and the T clock to Q of the external device, the trace delay, we have to estimate and provide that delay also as the constraint. Only then we can ensure that the outputs are taken into account. Similarly, for the constraining the output puts, we have to give set output delay. That is for maximum and for minimum. For example, this is our last flip-flop. That means you have the flip-flop here, it is ready. And from here it goes out. That means there is one more register which is outside. That means reg to output, if you see, that output goes to a register. So we have to constrain that also. So by providing those set input delay and set output delay only, you are able to constrain the entire design. So how are we going to solve that? When you say the same design, what we can do right now, I have applied only the clock path. Now you can go to the constraints and see here report unconstrained paths. If you see here report unconstrained paths, it shows the input to reg paths as well as reg to output paths. It shows they are not constrained. How are we going to solve this problem now? Go to reports, go to constraints here, and then go to set input delay. With respect to which clock, we have only one clock. I need to provide a maximum value, and then I can come up with some value. For example, I say 3 nanoseconds delay. What is the target that I am going to apply to all the inputs? That means I need to ensure that all the inputs, whichever is available, I will have some value. So I write here on targets, I say all underscore inputs. Okay, I take all the inputs, and for them I provide this value, which is the 3 nanoseconds value. And with respect to which clock you say, with respect to the clock CLK, I provide that value. You're able to see that it is taking the set input delay hyphen clock with respect to this. Similarly, I can apply the set input delay, the minimum value with respect to the same clock. I can say clock And then I have clicked the minimum here. And then, for example, I have some nanoseconds. And then the targets is all the inputs. That means, and then I provide this logic here. Similarly, I need to apply for the path from reg to output. How do we apply that? Set out delay. So that means from register to output, I just came up with some value, maximum value. I say 1 nanosecond. And then I just say here all underscore outputs. For all the outputs which goes here, I provide that value. Now I say delay value maximum with respect to which clock? With respect to CLOCK. Play that. And similarly, I have to go back and then play the set output delay with respect to the clock and say minimum and say delay value, for example, 0.5 some value. And then I say all underscore. And then run. So I have given some value. Right now we can able to see whether the design is constrained properly or not. We can say report clocks. And then I can say report unconstrained paths. Earlier, the unconstrained paths, it showed that all input to reg paths are not having any value. But then now you could able to see that the paths I have given the input to reg path some value and reg to output paths I have also provided the value. So when you have provided the constraints for register to register path, input to reg path, as well as reg to output path, I could able to ensure that the design is meeting time. So what is very important for us is here, have you constrained all the paths in the design? So first we have constrained the combinational logic block I showed you. Then have we constrained input to reg path? Yes. Have we constrained register to register path? Yes. And then have you constrained register to output path? So we have constrained all the 4 paths. Along with that, what do we have is called as the false paths and multi-cycle paths. We'll understand the concept, and there is a small lab on the multi-cycle path demo. That is our second lab. I will show the demo of that also. Let us understand that in detail right now. So now you have an asynchronous paths. You have asynchronous inputs where you have clear and reset. When you develop a code, very long code of a D flip-flop with asynchronous reset, you will have the asynchronous clear or preset pins that are available. So that also need to be taken care while performing timing. So I have shown you all this information. How do we check the setup and the hold values? So we'll understand the SDC timing exceptions. In the timing exceptions, we have the false paths and multi-cycle paths. So what is a false path and what is a multi-cycle path? We will get into the details. When it is a false path, that means we are going to understand that you have a design in which we need to be very clear that that particular logic is not going to happen. But then it is a particular path in which there is no logic that is available. But then the tool will identify that it is the longest path. So what are the cases? Let us take one small example for it, and then we will get into the details here. Let us take the example here. You could able to see that there are 2 multiplexers that are kept here, but then both multiplexers have the same select line. Now you could able to see that when the select line is 1, right, you could able to see when the select line is 1, now I can able to see that this A, this C, C1, C2, this will get enabled. But when the select line is 0, then B, B1, B2, then C out will get enabled. But then you could able to see that there are 4 paths. What are the 4 paths combinations you have when you say? You can take A, C, C1, C2 out, then A, C out is there, then B, B1, B2, C, C1, C2 out is there, and then B, B1, B2, C out is there. There are 4 paths. But then how many paths are valid when you say only there are 2 paths? But the STA tool will see that from the input to output, there are 4 paths, it will say. But how many paths are false paths here when you say there are 2 false paths? So it is our responsibility to tell to the tool that is a false path. Don't compute timing for it. Otherwise, what will happen? The path which is taking the longest path, it will take as a critical path. By mistake, if that critical path is a false path, then the entire timing will be wrong. So in these situations, it is always recommended to apply the false path commands effectively. That's one specific example which is shown to you. Okay. Exactly in the similar case, you could be able to see that there are some logic. There is a select line. We have to be very, very careful with it. So the paths in a design that physically exist but will be never exercised by the circuit is called as a false path. So these paths have no functional purpose and do not need to be constrained. By mistake, if we constrain, it will be a problem. You don't want. So that means you can tell the tool that set underscore false underscore path and say that whichever starts from this place, you set as a false path, so that it won't compute timing analysis for those paths. So specifying a false path removes it from timing analysis. That is very, very important for us. And another exception what we have is explained as a multi-cycle is important for us. As I explained to you, when it is a multi-cycle path is a path which takes more than one clock cycle to propagate the data from one flip-flop to another. So if you take more than one cycle for the data to propagate, so in that case, it is very critical and important to apply that as a multi-cycle path. There are commands which we are going to apply during our lab, but then it is essential and important to understand the multi-cycle path behavior. So you could be able to see there is a default behavior. We are expecting that from the launch flip-flop to capture flip-flop, it will take only one clock cycle. But there are chances that it can take more than one clock period to launch the data. So if there are situations where there is a multiplier in between, there is a multiplier and an accumulator, then what happens is then every 4 cycles, the multiplier will provide the output when we say. Then it is very critical and important to understand from the RTL background that whether that path is a multi-cycle path. This is a slow logic path. So that is very important for us to understand, and appropriately we have to apply the constraints. Now you could be able to see that it takes 5 clock cycles to take the data from one flip-flop to another flip-flop. If I say 5, that means it takes 5 clock cycles, which is very, very important for us. All right. Now, how do we approach that multi-cycle path? Is you have to say from, and then you have to say setup. How many clock cycles, for example? How do you know that these many clock cycles? Because we know the data path delay. For example, you wanted to constrain for 5 nanoseconds, but the data path delay itself is 7.7 nanoseconds. Then we have to give 2 clock periods because we should give at least 10 nanoseconds, so that 10 minus 7.7 will be a positive value. Similarly, this is only for the setup. And then you also need to give for hold. So you have to give for setup analysis, and then you also need to give for hold analysis. Let us take 2 designs here. First design is having 50 megahertz first flip-flop. The second flip-flop is sourced with 100 megahertz. There are 2 clock cycles. And then the second one is like first flip-flop is sourced with 100 megahertz, and the second one is 50 megahertz. And the question is, which one is a multi-cycle path? Which requires a multi-cycle path constraint, whether the first one or the second one? Do you have any answers? Okay, the answer is the design one. Okay? Because it requires a multi-cycle path of 2 clock periods for the setup and multi-cycle path of 1 clock period for the hold. Because 50 megahertz to you could be able to see there are 2 clock periods that are required to reach this. Because this is the 50 megahertz frequency and this is 100 megahertz. Design 2 does not require it. So since the design 2 receiving the register is having off as fast, so you need not to worry about that. No multi-cycle path required for higher frequency to lower frequency, whereas the multi-cycle path is required from 50 megahertz to 100 megahertz. Right. Now we will again go back to the quarters, and parallelly we can also go through the second lab. What is present in the second lab? We'll understand that in detail. So we'll move into that. This is the multi-cycle path example. In the multi-cycle path example, we are going to see that you are going to take 2 the designs in which you have two clocks. One is the 333 megahertz clock, and the other one is 666 megahertz clock. First, we are going to open the design and see what is the violation. Then we are going to set the multi-cycle path constraint and ensure that the design is meeting timing. After applying the multi-cycle path for setup and hold, and then check whether the design is meeting timing. And then we can save the constraints if you want. That is optional. Now I'll go back to the lab again. You have one more example where the timing analysis is specified. Go to the design files here. You can able to see multi-cycle path.qar. Copy that. Create a new folder in this case and say multi-cycle _1 I create. And inside this, I paste this. Okay, now I can come to the quarters once again. I close this project. If you want to save the SDC file, you can save it. If you don't want, you can leave it that. I say open project. And then I can say in the C drive, multi-cycle. One. Inside that, I have the multi-cycle part. I can open that design. You could able to see there are two clocks in this design. One is the always at passage of clock 333 megahertz. Other one is always at passage of clock 666 megahertz. That means you have twice the clock that is available here, 333 to 666. Let us compile the design and then we'll go to timing analyzer and see what is the violation, and then how are we going to fix that with the multi-cycle path commands. We will see that. Meanwhile, you can go through the manual here. What is available here? First, we are going to open the timing analyzer and see what is the error. You're able to see when we check the setup and hold the timing summary from here. The setup fails, but the hold passes. So since the setup fails, what we are going to do is we are going to apply the multi-cycle path constraint to design, because we need to wait for 2 clock cycles before getting the data to the sum register. So to do that, we just go to set multi-cycle path, and then clock 333 megahertz to clock 666 megahertz, we are going to give 2 clock cycles delay. So after providing that, we run this command, and then we set the same for hold, then check for violations. Now go back to the tools and then to the timing analyzer, and then create the timing netlist. You can open that. Now we can check for the clock, report clocks, and then you could able to see there are 2 clocks. Then you can check for violations. Report timing, and then you can able to see the timing report here. So the launch clock is 333 megahertz, and the latch clock is 666 megahertz, and then you could able to see that from this launch clock to latch clock, you have the violation. How are we going to fix that? Data arrival time is what, and data required is what. You could able to see that. Definitely it won't. So how are we going to solve this problem? We are going to give 2 clock cycles delay here. Again, go back to the constraints. Earlier we have seen create clock, set input delay, set output delay. Then we have seen set max delay, min delay, and false path. Now we have multi-cycle. You can click set multi-cycle path, and then you can say what is the setup value. So -from, and then you can filter the clocks, which is 333, right? Okay. And then 2, you can filter it here. List the clock 666, bring that this place. And then what is the value you are going to provide is 2 clock cycles, and then say run. Finally, go back to the constraints once again. Go to the multi-cycle path, from, and then you can say list 333, and then say OK. Instead of setup, you have to click hold, and then go to the 2. List that 666 megahertz, and then say OK. Right, from 333 to 666 megahertz, hold we are going to do in the launch, so therefore it is 1 clock cycle, whereas setup is done in the capture, so it is 2 clock cycles. Say run. we can check for timing. So now you could able to see that the design is meeting because the requirement changes. The slack is positive. So based on that, you could able to see what is the statistics. Earlier, it was a different relationship. Now it is a different relationship. You could able to see the requirement changes between that. These are the two labs that is provided to you, and the paper and pencil exercise solution is provided to you for reference, and you can go through that in the manual. And what are the different ways you can refer, that is also provided with the links. So we will share this analyzer manual with you, in which you could be able to see lab 1, which is the project setup, which I have showed you with the counter example, similar case. Lab 2 would be on the applying the timing constraints for all the designs, and the lab 3 is the multi-cycle path example. So now you could able to see that the design is taking the effects. Then we could able to see here. What is very important for us is the clock effects, where you could able to see there are different latencies. One is called as the network latency, other one is called as source latency. Source latency means from the output right to the FPGA port or pin. Network, when you say inside the FPGA, but when we say latency, that is the addition of both source latency plus network latency. Both we call together as the latency. So it is the delay between the clock definition and its source is called source latency. Network latency is in between the clock to the first flip-flop. That is the delay that we call that as a network latency. Right, so all those things will also be taken into account, because these things we have subtracted, but then we didn't take care during the design. That's what the definition is provided to you. What is clock uncertainty? When you say there may be a skew, that's what I explained you. Difference in arrival of the clocks between two successive registers, we call that as the uncertainty. And then jitter, we have the deviations from the exact defined period. Right, so these are the things which we have seen. I will pause here. If there are any questions, I will take it. Otherwise, I will leave this stage to Bhaskar. Thank you all.
Thanks, buddy, for a wonderful session.
Thanks, Bhaskar.
Thank you, Padmanabhan.
Currently, I am unable to share my screen. Yeah.
Just a minute, sir. Just a minute. I'll give you the rights.
So thank you all. Please practice the labs what is provided to you. Are there any issues? Please contact us. We are ready to help you out.
So thank you, sir. I may request you to please, if possible, sir, you can stop sharing the screen so that we can share the rights with Bhaskar, sir.
Yes, I have done that. Yeah, please.
Yeah. Okay. Thank you, sir. Thank you for such a wonderful session. Good afternoon, participant. We are starting with the second session of day 2. The second session of day 2 is going to be delivered by Mr. Bhaskar Venugopal. He is the system validation expert at Intel Programmable Solution Groups. He holds a dual master degree in VLSI and Applied Electronics from Satyabhama Institute of Science and Technology, Chennai, and Bharatiya University, Coimbatore, respectively. Bhaskar sir has about 15 years of experience in front-end design, and he worked on design and development of a variety of IPs, subsystems, and SOCs that caters to the network, high-speed compute, and AI solution. Bhaskar sir has also rich experience in ASCII and FPGA and has worked on debug architecture for the next generation highly complex ASCII systems. Bhaskar sir is more passionate to teach and conduct classes in the area of VLSI and associated with the emerging areas to the student and the technical groups. So with this, we would like to invite Bhaskar sir to please join us and start with the next session. Bhaskar sir, we have given you the presenter right also, so you can just check if you are able to share the screen.
Yeah, I'm presenting my screen. Let me know if
Yes,
people
sir,
can
your
see my
screen
screen.
is visible.
Okay. Yeah, thanks for the introduction. Very warm welcome to all the participants, dignitaries who have joined this online session. And thanks to Intel and academic sponsored program. Thanks for giving me an opportunity to take this session. So in this session, I will be talking about clock domain crossing. In short, in industry, people call it as CDC, clock domain crossing. So let's see what is meant by clock domain crossing. Basically, at a high level, okay. Basically, we have today you might have seen multiple SoCs, VLSI chips, which operate on multiple clocks. Though from the user point of view, the software, the underlying software takes care of everything. But if you go deep down into the hardware component, you will see multiple blocks. You will see multiple partitions, multiple blocks put together to form a IP or to form a SoC. These SoCs operate at different clocks. So when you want to transfer data from one clock domain to another clock domain, there are certain techniques. There are certain issues which, as a user, we have to take care during designing a SoC or a ASICs. Okay, this applies for FPGA as well. So today, in today's session, we will discuss about what is meant by multi-clock design, and what are the issues one will encounter while doing a data transfer from one clock domain to another clock domain, and how to address those challenges. What are the reliable, robust clock domain crossing techniques that is used across industry as a standard practice? We will discuss about all those things. So in this example, you see, let us consider this outer box as your SoC. SoC stands for system on chip. Let's say, for example, this is a SoC, and it has some submodules or partitions. Say, for example, partition A, B, C, all the way till H. Okay. Now you see here in this particular block diagram. So you see here in this particular block diagram, the partition A, C, and G, these three are associated with clock domain 1, clock 1. So that means these three modules are operating at clock 1 frequency. Then B and D, these are operating at clock 3 frequency. E and F are operating at clock 4 frequency, and H operating at clock 2 frequency. Now you see there is an interaction between these modules. The output from A goes as an input to B. The A module is sending its output on one clock 1, but B is supposed to consume it on another clock, which is clock 3. Similarly, if you see C to D, similarly from D to E, you see there is a domain crossing from clock 3 to clock 4. We don't know the relationship now. What is clock 3 frequency? What is clock 4 frequency? What is the phase relationship between these two? We don't know. Okay. Similarly, clock 2, you see here, it is crossing from clock 1. It takes this H module, this H partition, receives its inputs from clock 1 domain, performs its compute function, whatever functionality it is supposed to perform at clock 2, then provides its output to F domain, which is clock 4. So here across this, if you see the data, the input data which enters your chip, which enters your SoC or your partition, is getting processed by various modules that operates on various clock domains and gets propagated to next submodule, which operates on another clock domain and finally comes out. So in this particular design, you see there's a questionnaire here. How many clocks do you see in this design? We see there are 4 clocks, clock 1, clock 2, clock 3, and clock 4. Okay, now let's see what is meant by clock domain crossing in deep. Okay, So now there are two types of clocks. One is synchronous clocks, another one is asynchronous clocks. In synchronous clocks, we know the frequency and phase relationship. For example, for any design which requires a clock, the clock will be generated by the on-chip oscillators like circuits like PLL or on-board oscillator. In the board, you will have your chip, and in the board, you will have a clock generator circuitry also. That may provide your clock. If you are building a complex SoC, ASICs, instead of you relying on external, keeping the clock from the onboard, we will put clock inside the SoC itself, in the ASIC itself, in the FPGA itself, so that within a chip, you go configure the PLL, then that PLL will give the desired clock frequency. Now, to understand the phase and frequency relationship, if you know, for example, let us consider this PLL-A, which is a phase lock loop module, which is a clock generator module. This PLL has two outputs. Each output is named as clock 200 and clock 100. Now, going by this naming convention, let's assume that this first clock is 200 MHz clock with 50% duty cycle. The second clock is 100 MHz clock with 50% duty cycle. Now, you see the root, these two clocks are generated or derived from this same PLL, which is PLL-A. So we can call these two clocks as synchronous clocks. The reason is we know the phase and frequency relationship. This clock 200 is 2 times faster than clock 100, and these two are originating from the same source, which is same system PLL, same PLL-A. So this can be called as synchronous clocks. You see another PLL, which is PLL-B in your design, and this is named as H clock 100. Going by the naming convention, we can consider this as a 100 MHz H clock. These are just the clock names, which is the output of the PLL. Now, if I want to say what is the relationship between this H clock 100 and this clock 200, I can tell from the frequency point of view, H clock is 100 MHz, whereas this clock 200 is 200 MHz. But today I don't know the phase relationship between these two. There is no guarantee that both of them will start with logic 0 phase when we power on the SoC or when we power on the board, or both of them will start at logic 1 phase. So we don't know the phase relationship. And moreover, this clock, though it is 100 MHz clock, I cannot say this clock 100 and this H clock 100 both are same, because this H clock 100 is originating from another PLL-B, whereas this clock 100 is originating from PLL-A. So with respect to this diagram, we can say this clock 100 and H clock 100, these two are asynchronous in nature, because though the frequencies are same, but their source is independent. They are not originating from the same source. And we also don't know what will be the phase relationship. So these kind of clocks are called as asynchronous clocks. Asynchronous clocks, independent frequency and phase relationship with respect to one another. Now, why should we check for clock domain crossing? What happens if I don't check? What will be the consequence? What will be the impact? So this is what we are going to discuss in this slide. Unsafe clock crossing leads to metastability, data loss, and data incoherency. So when we say metastability, say for example, I have a sender. Let's take a small analogy here. Say I have to work with some neighbor person. He has to say he will be talking, he will be communicating to me in he knows only Japanese, and the other person, he knows only Chinese. Now there should be some translation mechanism where these two people can communicate efficiently. So we need to use a kind of translator or some intermediator who can understand what the person A is communicating and properly translate it in the language which person B can understand. Similarly, vice versa. So similar way, you apply the same analogy here. If you want to transfer a signal from one module to another module, which are operating on two different clock domains, we have to ensure that proper clock domain crossing structures are in place so that your functionality is addressed cleanly and correctly. Okay, so if you don't take care of this clock crossings, it leads to metastability, data loss, and data incoherency. Okay, we will talk about these 3 points in brief in the upcoming slides. Then clock domain crossing bugs can cause serious design failures. Most of the chips which you see, which fail in one or the other scenarios, either while we are bringing up the SOC or while we are testing the SOC before giving it to the customer, or even at the customer place, most of them would be due to clock domain crossings. These, because all the scenarios cannot be validated and it's time consuming, and we don't know how the customer will use all these SOCs put together. So though there are robust mechanisms to catch all these CDC bugs, there could be some misses. A survey which was conducted a few years ago, it said that most of the silicon issues which were found are due to clock domain crossing, and these a issue which was found late in the game, it will have its own consequences. So clock domain crossing, we have to pay more attention and ensure that we have reliable clock domain crossing structures implemented so that all clock crossings can be robust and reliable. If let's say you have found some issue, now to debug this in the silicon, when I say silicon, say you have designed your SOC and it has been manufactured, it has come back from the manufacturing, now you are validating it for the functional correctness. To debug these CDC issues, it's very time consuming and it's very hard to find these kind of bugs. So a rigorous test methodology should be in place to ensure that all clock domain crossing paths are thoroughly exercised for all sort of corner case scenarios. Okay, for designs where we don't know the relationship of the clock, then we need to come up with the strategies for transferring of information from one clock domain to another clock domain. Now let's try to understand what is clock domain crossing. Now let us see this. Let us talk about this diagram. Okay, this is a flip-flop. Flip-flop A. Okay, it has its D input, Q output, and a clock C1. Similarly, I have another flip-flop which is called as flip-flop B. It has its own D input, Q output, and output B, and it has its own clock. Now you see this flip-flop A is operating on clock C1. Let's assume, for example, this is 100 megahertz. Now there is another flip-flop which is the destination. This is a source. The first one in the highlighted in the blue color, is a source, and this red one is a destination. This destination flop is operating on C2 clock domain. For example, let's consider this is 500 megahertz domain. Now you see flip-flop B operates 5 times faster than flip-flop A. But now from this flip-flop A, I want to transfer a data to this flip-flop B, which is a 1-bit signal. Now how I could transfer this? Okay, what will be the problem if I don't have any synchronizers? Or what kind of synchronizers I should use? How do I reliably transfer this data A all the way to this D input of the second flip-flop, which is operating on another clock, which is C2? Okay, so this is clock. This is a typical example of a clock domain crossing. Okay, here the objective is to transfer data from one clock domain to another clock domain. C1 drives flip-flop A, C2 drives flip-flop B. Okay, the signal which is output from flip-flop A, which is called as A, should be transferred reliably to flip-flop B's D input. Okay, this is clock domain crossing. Now we said in the previous slide, we saw what will be the consequences if we don't examine the clock domain crossing. We will hit into metastability, then data loss, then data incoherency. Okay, now let us talk about a phenomena called as metastability. Okay, it is a metastability is a phenomena which happens when the input data is not stable, or in other words, if your D input of the destination changes very close to the active edge of the clock, then it is highly possible that your flip-flop B will enter into metastability state. Okay, that means in the previous session you have Padmanabhan has explained about setup time, hold time concepts and all very nicely. So there is a window of period. There is a window before the rising edge of the clock and after the rising edge of the clock, where it is expected that your D input should be stable so that the destination flop can sample the value reliably. Okay, if your D input, if your input is changing within that window of called a setup window or hold window, it might lead to metastability. Why this happens? If you consider this flip-flop, which is implemented as a chain, as a series of, as a cross-coupled NAND gates, you need some amount of time for the D input to propagate to the internal structure of your flip-flop and get latched on the positive edge. Then on the negative edge, it will be, the latched value will be driven to the Q output. So to latch this, for the first latch to close, to latch its value properly, the data should be held constant. That is called as setup window. Similarly, once the second latch becomes transparent, that will drive the latched value towards the output. That time your hold, that is called as your hold. So if you want to have a reliable data transfer with the correct value, we need to ensure that the D input should be stable within the window called as setup window and or hold window. Okay. If there is a violation, which means violation means if the data changes in this window, then your D input is, that means your D input is still changing. It is not constant. It is ramping up either from 0 to 1 or it is ramping down from 1 to 0. That means it is not stable. In that scenario, your flip-flop B, it could not able to predict what this value should be treated as, whether it should be treated as logic 0 or logic 1. So it gets confused, and it might take one more clock cycle for and to understand what is the stable value that it should drive on the it should give on the Q output. This unstable input at the D, which is violating the setup or hold window, is called as metastability. This phenomenon leads to metastability. Okay. Now let's see what is metastability, clearly explained in this waveform. Let's see, for example, this is a C1, which is a clock. Okay, the clock transitions from 0 to 1 here, and C2 transitions from 0 to 1 here. Okay, in ideal world, the clock is not really a square wave. It will be a kind of ramp only. Okay, it will go from 0, then it goes like this, then comes like this. Okay, it will not be a perfect square wave. Okay, now you see this data A. This data A is the output of the first flip-flop. Now it has to be sampled reliably by the destination flop FB. Now you see the FP will sample the data with respect to rising edge, positive edge of this C2 clock. Now you see the positive edge is here. This is the place where the clock is 0, the polarity is 0, then it is rising. So in this active edge, the flip-flop will sample the new value. So in this case, but when this rising edge has occurred, you see the value of A. The value of A is not even 0 or not even 1. It is transitioning. You see here this steep, this slope. It is rising from 0 to 1. Now, exactly at this point, wherever my cursor is, now what is this? What is the threshold value? What is this value should be treated as? Whether it should be treated as logic 0 or it should be treated as logic 1. This is where your flip-flop gets, your destination flop gets confused, and he doesn't understand clearly whether this should be treated as logic 1 or logic 0. So the consequence is the B output after a couple of after few nanoseconds of time or few picoseconds of time, it might settle to a new value 1, or it might settle to new value as logic 0. But it requires time. This dotted line, this window of time is called metastability phenomena, where your flip-flop takes some time to understand reliably what is this value to be treated as. Based upon the technology library, let us assume exactly where my cursor is. This is 0.8 volt, for example. Now, in the technology library, what is 0.8 volt? Anything above 0.6, let us consider, for example, anything above 0.6 should be treated as logic 1. Anything below 0.6 should be treated as logic 0. So in this case, the destination flop will sample this as logic 1. If the threshold value is different, then it will sample it as logic 0. But the fundamental point, what we have to understand from this diagram is, here your input is not stable, which it is transitioning. This is clearly a violation, because if I put a setup window here and a hold window here, within this window period, my input should be stable, but it is not following that property. Here it is changing. This will lead to this metastability phenomena. Okay. Now, there are no ways to avoid metastability, but there are chances that we can reduce the occurrence of metastability. Okay, there is no way you can avoid metastability completely. Okay, but you can reduce the occurrence of metastability. How? There are some special circuits which are called as synchronizers. A kind of what do you mean by synchronizer? A kind of circuit which allows some time for the metastability value to settle down to a known state, so that the destination can capture it with a correct value. So now you see here these two flip-flops. These two flip-flops, DQ and DQ, this is a synchronizer circuit. Okay, please remember that this FB, this is a destination flop. In this diagram, I have not shown FB. The destination flop is not shown in this diagram. Only the synchronizer structure is shown. Okay, in this case, the synchronizer is a two flip-flops connected back to back, and these two flip-flops should be placed placed close to each other. Okay, let me explain why we want to place this close to each other. Okay, so the special circuits which are widely used to transfer a signal, especially a 1-bit signal from one clock domain to another clock domain, is this multi-flop synchronizers. People call it by different names: multi-flop synchronizer, dual flop synchronizer, dual rank synchronizers. But the fundamental circuit is two flip-flops connected back to back, both placed together. In the technology library, say you are building your SoC or FPGA or ASIC in a 10 nanometer technology or 7 nanometer technology, the library vendors provide these as one single cell. Okay, so you can use those single cell where the library vendor ensures that these flip-flops are faster, have higher gains, and they are placed very close to each other, so that they are prone to metastability issues. So that if a D input is if the A input is fed to this D input to the first stage of the synchronizer, though the first flip-flop may enter into metastable, the second flip-flop, it has one clock cycle period to settle the value. So within that one cycle period, the B output from the first stage of the synchronizer will be settled, so that the second flip-flop within the synchronizer will always see a stable value. So it will sample either 0 or 1. Now the downstream logic, which is flip-flop B, which is sitting somewhere here, it will also see a valid value, which is 0 or 1. It will not see any metastability value. So this, by using this two flop synchronizers, we can reduce the metastability. Okay, basically these synchronizers, what it does, it allows the oscillations to settle to a known value, either 0 or 1. Okay, so whatever I discussed, that's what I have added here as a points. So to reduce how can we reduce metastability? We can use special structures called synchronizers before the destination domain. Okay, synchronizers allow sufficient time for the oscillations to settle down. Okay, this synchronizer output always ensure that the stable valid value is sampled by the destination flop. Okay, a commonly used synchronizer is a multi-flop synchronizer. You can add one more stage of synchronizers, but it will add latency to your design. Okay, but there is nothing harm. But there is something called as MTBF, mean time between failures, which is a formula derived out of your process technology and your data rate and your clock frequency. Based upon this MTBF, the calculation will give you how reliable your system will be. For your system to fail, how many years it will take for your system to fail. Okay, so based upon that calculation, you can decide whether two flop synchronizer is sufficient or you want to use one more flip flop. Okay, for frequencies greater than 2 gigahertz, we recommend to use 3 flop synchronizers. For frequencies, and by the way, this is for 10 nanometer technology. Okay, for frequencies less than 2 gigahertz, 2 flop synchronizer is more than sufficient. Again, remember, this is for 1-bit signals only. Okay. Okay, now here you see from this diagram, you have 1-bit information which is coming from clock domain 1, and this 1-bit information has to be sent reliably to the destination domain which is operating at clock 2. In between these two, I have placed this synchronizer structure. Okay, this synchronizer structure will efficiently reduce the metastability phenomena, and it will ensure that the destination domain sees always a valid stable value. Okay, now in this case, let us consider this asynchronous clock crossing. This is a 1-bit information, and with the assumption that this clock 2 frequency is higher than clock frequency 1. Okay, that means clock 2 is faster and clock 1 is slower comparatively. Okay, and multi-sampling is not an issue, or 1 or 2 sample missing is also not an issue. Let me give you one example. Say, for example, you have a memory in your design, and you are writing something into the memory reliably. Okay, for example, data A5. Now you are reading the memory. While writing the memory, you are computing a parity check, and you are putting a parity bit also in the memory. While reading back the contents from the memory, you want to check whatever contents you have wrote is what you have got while reading. So while reading, you are again recalculating the parity. That time some bit got corrupted. You got a parity error. Now this parity error is a kind of status information. Now this information has to be communicated to the host processor or whatever logic, which can take some corrective action. So this parity error bit, now it will be a level signal. Once parity error has occurred, unless you go and correct that particular bit, the parity error bit will remain set to 1. Now this logic 1 should be sampled by the destination flop. In this case, either the destination domain samples it only once or it samples for more than one time, it's not a problem. All you want as a functionality is, as soon as the destination sees the parity error, its job is to sample it and communicate that information all the way to the processor or to some interrupt logic, whatever it is. Okay, and it doesn't matter whether it samples it as soon as the parity error has occurred within the first cycle or within the second cycle. Okay, so it doesn't matter. So that is what we are trying to explain in this slide. You can reliably transfer 1 bit of information where you don't have where multi-sampling or missed sample is not an issue. Then you can use 1 bit. You can use this structure, which is a 2-flop synchronizer, to transfer from one clock domain to another clock domain. Yeah, here is an example with the waveforms. Let's consider this clock 1, which is a sender or source. This clock 2 is a destination or receiver. We said clock 2 is faster than clock 1. Now you see clock 2 is faster than clock 1 because here you see one period, one cycle. Within that window, you see at least 1.5 cycles here. So obviously this clock 2 is faster. Now this clock 1, which is a sender, is transferring a 1 cycle pulse. You see here, this 1 bit information is a 1 cycle pulse. It is high for only 1 clock cycle. When I say 1 clock cycle, this is active high, stays high, coming low, and then this is 1 clock cycle period. Okay, within this 1 clock cycle period, I have a sender whose information is high for 1 clock cycle. After 2, again it goes low for 2 clock cycles, again it becomes high for 1 clock cycle. Now this 1 bit information, which is info underscore bit 1, is the information which sender is transmitting, and the receiver has to sample it correctly. Given by the constraint assumption, we said that multi-sampling is not an issue in destination domain. Okay, so now you see here in this clock 2 active edge, the value seen is 0. So you see info bit 1 underscore q is 0. On this rising edge, you see the value as 1. So the q output become 1. Then again on the second rising edge, the value is still 1. So you see again it's 1. Similarly, this is the output of the first stage of the synchronizer. This is the output of the second stage of the synchronizer. Basically, a flip-flop adds 1 cycle delay. So you see the second flop output is going high at this point of time. Now you see the sender has transmitted a 1 cycle pulse exactly, whereas in the receiving domain, you see it is high for high for 2 clock cycles in this case. Okay, but it is still not a problem, because if your design says it's not a problem, then it's okay. But if in the destination also, if you want exactly 1 cycle pulse, then you need to add some extra circuitry to detect a pulse, okay, to detect a rising edge, okay. So now let us consider another scenario where I want to do a 1-bit signal transfer, which is from high to low frequency. That means your sender is faster and the receiver is slower. Okay. In this case, the sender should ensure that the signal is held long enough so that your slower module can sample it correctly. Okay. Let's assume you have a sender which is operating at 200 megahertz and you have a receiver which is operating at 50 megahertz. So in this case, if you are sending a signal which is at 200 megahertz, if you send a 1-cycle pulse, the destination will not even see that pulse. So we have to ensure that the pulse that which the sender is sending is held long enough so that at least one active rising edge of the clock of the destination domain sees it so that it can sample it correctly. Okay. The point here to remember is that if you are transferring a 1-bit information from high frequency to low frequency, then you have to ensure that the signal that you are transmitting is held long enough so that the destination samples it correctly, and make sure that the destination should not sample any glitchy signal. Okay, always it's recommended to send a flopped version of the signal to the destination. Okay, a flip-flop acts as a glitch filter. Okay, if you send directly a combination logic output, if any of the input changes suddenly, then your combination output will glitch. That glitch will confuse your destination module. So it's always recommended that there should not be any combination logic before your destination module. Directly the synchronizer output, which is a flip-flop output, should feed your destination directly. Okay. But again, analyze carefully the nature of signal and the clock domains from where it is arriving and where it has to be transmitted, and see which is the efficient synchronization scheme. Okay. Now let's consider another scenario where I want to transfer signal from low frequency to high frequency. Generally, in general, low frequency to high frequency is not an issue. Only thing is, if the destination wants to ensure that only 1-cycle pulse is captured, then you need to have some extra circuitry. Okay, like what we discussed in 2 slides before. Okay, so the recommendation here is that always use a flopped signal to ensure stable value is sampled. And even though I say it's a low frequency, let's consider this second point where your sender is 95 megahertz. Your source is operating at 95 megahertz and your destination is operating at 100 megahertz. You will have only a small difference in the frequency. Okay, but this will have a very big impact if you don't synchronize the signals properly. Okay, because of clock skew and the jitter, you don't know when these two clocks will when the active edge of these two clocks will come. If they come very close by and if your data violates the setup or hold, then it may cause to metastability. So in that case, it's always recommended to ensure that you stretch the signal until one of the active edge of your destination domain sees it, so that it can ensure robust sampling. The destination can sample a robust valid signal, settled valid signal. Okay. Multi-sampling of signal should not be an issue for the receiving logic using a double flop logic, else special logic is needed for the domain transfer. Yeah, if you want the signal, just the destination to sample the signal, then you no need to have any extra circuit. If you want to ensure that destination also sees exactly 1-cycle pulse, like what the sender has sent, then you need to add some extra logic. Okay. Basically, a pulse detector or a rising edge detector circuit is to be added. Okay, so for what we have discussed is, if I want to transfer a 1-bit information, which is a control information, like for example, memory write, memory read, chip select, or some kind of state machine signal, which is a 1-bit information. What happens? Okay, in logic design, whatever functionality you design, you does not have only control signals. You have wide data bus where your data gets transferred from one module to another module. Okay, or you have a wide address bus which gets transferred from one module to another module. So in that case, when your information is a group of signals, which is a bus, what kind of mechanism can we use to transfer domain crossing. In this case, let's say, for example, I have a 32-bit data plus 4-bit control signal, which I want to reliably transfer from clock domain 1 to another clock domain 2. In this case, can we use double flop method? Answer is no. Why? Okay, two reasons. One is, first point is, from the functionality point of view, in the very beginning, we discussed that there could be data loss. Okay, what will be the consequences of metastability? Oh, sorry, CDC, metastability, data loss, data incoherency. Okay, when you are transferring a group of signals from one domain to another domain, we cannot use a double flop method, because in this case, you see, there are 36 signals. So if you want to transfer all these 36 signals bit by bit using a 2-flop synchronizer, putting here, okay, you are, first of all, you are increasing the gate count of your logic. Okay, basically you are increasing the gate count in your design, you are increasing the flip-flop count. And another thing is, this double flop method is not a robust method for transferring a group of signals. Say, for example, you are transferring a data, even though you are using the double flop synchronizer cell from the same library and instantiating it 36 times, there is no guarantee that all the 36 cells will behave identically in silicon. Okay, one may sample 0, one may sample 1, another may sample 1. So data coherency cannot be achieved if you use double flop synchronizers. Then what is the other alternative? We will discuss. Okay, there are three synchronizer schemes which can be reliably used to transfer a group of signals, which is bus. Your data bus can be 32-bit, 64-bit, 128-bit, 256 bits, or a group of signals which you concatenate together, and you want to transfer it to another domain. In such scenarios, commonly there are three methods which are widely used. One is called as mux based synchronizer, multiplexer. Okay, a multiplexer based synchronizers. Okay, then another method is a handshake synchronization scheme, and another method is queues or FIFOs, first in first out. Okay, let's talk about each of these in the upcoming slides. Okay, this is a mux based synchronizer scheme. Okay, now let me explain about this diagram. Let's consider, for example, in this diagram, I have 2-bit of information, A0, A1. I want to transfer 2-bit of information from this source, which is operating at C1 clock domain, to the destination, which is operating at C2 domain. Okay, now instead of me synchronizing this A0th bit using a 2-flop synchronizer here, I could do that, but there is no guarantee that my synchronizer will work properly or data coherency can be always achieved. There is no such guarantee. So in such case, then my functionality will go for I will have a functional failure. If my functionality is broken, that means my application, whatever I am running on the SoC, is broken. So in order to avoid that situation, what we do is to transfer a group of signals from one clock domain to another clock domain, we mostly prefer this mux-based scheme. In this, what happens is the sender, the source, along with the data, he will generate an enable signal, also called as valid signal. Okay, this will be typically, this is a control signal, which indicates whenever this control signal is high, when I mean high, whenever this control signal value becomes 1, it is an indication that whatever value is placed on this A0, A1 is valid value, and the sender can sample, and the receiver can sample these values. Now, instead of synchronizing these independent bits A0, A1, what we do is we synchronize this enable signal using a 2-flop synchronizer with respect to the destination clock. You see here, this enable signal is fed as input to a 2-flop synchronizer. This synchronizer operates on destination clock domain, which is C2. This first flop may enter into metastability, but the second flop input, this keyword, the second flop will always see a stable value, and at the second flops, the synchronizer output will be always a stable value. Now you see, this goes as a mux select input to the mux. Okay, now whenever this select input is high, then that time the new value will be sampled by the destination flop. Basically, this path A1 all the way goes to the D input of this flop. A0 all the way goes to the D input of the flop. Whenever the select signal is 0, you see the previous value is looped back, the feedback path. That means whenever this enable is high, the destination samples a new value. Whenever the enable is low, the destination holds the sampled value. But here the point to make note is, instead of we synchronizing individual bits, we synchronize the enable signal, and this synchronized enable signal is used as a select input of the mux. Whenever this enable signal becomes active, when I say active, whenever it becomes 1, it is the responsibility of the sender to ensure these data are stable at that point of time. When enable is high, that time if you change this A1 and A0, then it defeats the purpose of the synchronizer. It will again lead to metastability. Okay, so I think that's what he written. Yes, when enable sync signal is active, the source domain data should be held constant. Yeah, so basically you need to have a kind of state machine or something which ensures that unless this enable signal is sampled, synchronized and sampled properly by the mux select input, this data should not be changed. It should be held constant. This is one of the widely used scheme while we build SOCs or FPGAs or ASICs. When we do when we transfer clock data from one clock domain to another clock domain, especially a group of signals. Another scheme is handshake scheme. In this case, basically what we do is, we along with the information of data, we send a kind of request ACK kind of signals, which is again a kind of valid signals, which the sender will acknowledge. Once the sender acknowledges, then only we go and change the data on this. Okay, I have a diagram. Let's talk about it. Okay, in this example, you see the one shown in this dotted lines. This is operating at clock B. See, for example, here this is a flip-flop clock B operating on clock B. This 1, 2, and these 3 flip-flops are operating at clock B, and there is some FSM or some logic which is operating in clock domain B. The left-hand side, all these operate on clock domain A. You see, this is clock A, clock A, clock A. Okay. Now let's say, for example, this module, which is a source or a sender operating on clock domain A, is sending a 1-bit signal. That 1-bit signal comes from the flip-flop, which is called as SIG-A. Now this SIG-A is a kind of signal, which kind of acknowledgement signal, which is sent to a destination domain. You see here, now in the destination domain, these are the synchronizers, SIG-A Q1 and SIG-A synchronized. Okay, the synchronized output feeds the FSM. Now this FSM sends an ACK back to the sender saying that, hey, I got your acknowledge. Okay, I have sampled the data. Now I am sending you an ACK back. Okay, now he has sent an ACK back. Now this ACK is again a kind of 1-bit information, is synchronized to the sender clock domain, which is clock A. And once this synchronized signal is seen by this sender clock A domain, then he will change his output data SIG-A. Basically here, the fundamental concept here is, in handshake mechanism, basically we are exchanging, before sampling the data, we are exchanging a kind of information saying that, hey, the sender says, hey, I have put a valid data on the bus, you go sample it. Then B will go sample it. After sampling, B will send a ACK back to A saying that I have sampled, you go and update the data now. Okay, so this is a basic fundamental concept behind handshake mechanism. This is a very robust, powerful mechanism to do a clock domain transfer. Any number of bits, it's a very robust mechanism to transfer data from one clock domain to another domain. But the problem is the latency associated with this. If you want to transfer one chunk of data you see how many clock cycles it requires. The 2 clock cycles here for the destination to synchronize. Then the destination should sample it. Okay, then the destination should generate an ACK. The generated ACK should be synchronized by the sender clock domain. Then only the sender is allowed to change the data. So you see here, at least here 3 clock cycles, and then here 2 clock cycles. You cannot change your data unless 5 clock cycles. Basically, you are degrading the performance. The number of data bits that you can sample or that you can process in every clock cycle determines the throughput of your SoC or your ASICs. So in this scheme, though it is a robust scheme, but the performance wise, it is due to the handshake latency. Basically, the latency is introduced by these synchronizers, and the logic that generates the hack degrades the performance of your logic. So this scheme is not widely used. But in a scenarios where latency is not an issue, you can go ahead for this scheme, which is handshake based synchronization scheme. Okay. There is another scheme which is used to transfer data, address, or a packets or a group of signals. Okay, which is typically called as queues, or in industry we call them as FIFOs, first in, first out. Okay, basically the FIFOs or queues, these are an array of it has some control logic on the right side, and it has a control logic on the read side, and you have a memory element. Sometimes we use a memory, or sometimes we use a flip-flops. Okay, basically you will be writing the data into the memory in one clock domain, and you will be reading the data back from the memory in another clock domain. Okay, I have a circuit, let me explain about you. Okay, so in this, in general, most widely used clock domain crossing scheme is queues or FIFOs. Okay, now in this case, you will load the data into the queue. Basically, you will write the data into the queue from domain A, and you will unload the data from the queue from domain B. Okay, the queue status can be tracked in each domain with respective clock crossed control signals. Okay, let's see the diagram. Okay, queues are standard address or data path structures used to temporarily store or buffer the data, and it solves the latency problems between functional unit blocks. Okay, and this is a primary method for data transfer across clock domains. Okay, now you consider this as a memory element associated with some write logic and read logic. Okay, basically you are writing this data in, which is a bus information. Let's consider this is a 64-bit data. You want to write this data into this memory. So you are writing it, you are placing the data on the data bus, and you are asserting a write enable signal. We call the write enable signal as put. Okay, whenever this put signal is high for one clock cycle, whatever the data is present on the bus data in, that will be written into the FIFO. It gets latched into the memory element. Similarly, when you want to read the data out, you just give the read signal, which is nothing but get. In this case, you assert this read signal, get signal, then whatever address the pointer is pointing, that the data from that address will be placed on the output bus. Now the receiving logic can sample this data out, and it can do its processing. Okay, along with these two control signals, you see this is write and the write data, this is read and the read data. You see read is an input to the FIFO. You assert a read signal, then you get a data out. Okay, along with this, you see there are two control signals, two flags, status flags called as full or empty. Okay, you cannot keep writing into the FIFO because this is a memory which has some n entries. Say for example, this memory is 8 deep memory. That means you can write 8 words into the memory. Okay, so you should have a mechanism to say whether you have enough of valid entries to write into the memory or not. So you need to have a kind of control circuit which says whether the memory is full or you have some enough space to write. So this is a full status flag. Similarly, you are not supposed to read anything if there is no data. So you should have an indication to say that whether the FIFO is empty or it has some valid contents. Okay, so this first off operates on write clock domain. This second off operates on read clock domain. Okay, let's see a kind of okay. Now you see, let us consider this is a FIFO. It has 4 entries: entry 0, entry 1, entry 2, entry 3. Basically 4 locations. That means 4 n-bit words can be stored in each of this entry. Okay. So put pointer, get pointer, basically a write pointer and a read pointer. These are the address pointers, which is used to address which location we want to write or which location we want to read from. Okay. You see here, there are 4 entries. To address 4 locations, according to binary logic, 2 bits is sufficient to me. Bit number 0 and bit number 1 is sufficient to me. Bit number 0, 0, 0, 0 means entry 0, 0, 1 means entry 1, 1, 0 means entry 2, 1, 1 means entry 3. But you see here, I have used 3 bits. Why? Let me explain. Okay. Now let's see how this FIFO works through a kind of small animation. Okay. Now upon reset, okay, any sequential logic, you have to bring it to a known state. How do we bring it to a known state? Either it should initialize itself to a logic 0 or logic 1. Okay. There is nothing called as unknown in real-time silicon. Either it should be having a threshold value pointing to logic 1 or threshold value pointing to logic 0. So you have to initialize your digital logic circuit using a reset. Okay. Say upon reset, you have initialized these pointers, put pointer and this read pointer both to 0. Okay. So both are now pointing to address location 0. Okay. Let's, for a simplicity, let's consider the address as this is 0, address 1, address 2, address 3 in decimal. Okay. Now both the pointers are pointing to address location 0. Okay, consider this as an array of houses. Okay, first house, second house, third house, fourth house, each has unique address. If a postman comes and he wants to deliver a letter, in the envelope, he will just look at the address and he will go deliver it like that. Okay, now both the address are pointing to address 0. So now whatever data is placed on the data bus on the right side, the user has placed whatever the data the user has placed on the data bus, that data, once the write enable signal is asserted, will get stored into this location because the address is pointing to address location 0. Okay. Similarly, if a read is asserted, if a read enable signal is asserted, whatever data is here, that will come on the output bus. Okay. Now both the pointers are pointing to address 0. Now let's consider another scenario. Now the address pointer has incremented. Now it is pointing to next location, which is address 1. Okay. Now another write has been written, another word has been written into the queue. Now the address is pointing to entry 2. Okay. So before moving, okay, now there are 3 entries having a valid data in the queue. Address 0 has a valid data, address 1 has a valid data, address 2 has a valid data. Okay, so the FIFO is not full. I have still one more entry left. This location is not yet written. Okay, read pointer is still pointing to address 0. Now let me do one more read. Now my read pointer is pointing to entry 1. Let me do one more read. Now the read pointer is pointing to entry 2. That means whatever data is written by the right clock domain on these 3 locations, entry 0, entry 1, entry 2, those 3 data are read by the read clock domain. Now, theoretically speaking, we don't have any data in the FIFO. The FIFO, all these 3 locations are empty. This is also empty. Okay. Now, this is how we generate this is how we detect a empty status. Empty status is nothing but if your write pointer and the read pointers are same, that means it is the FIFO is now empty. You don't have any data in it. Okay. Now the write pointer is still pointing to entry 2, but read pointer is still pointing to entry 2, but write pointer has advanced and it is now pointing to entry 3. That means I have written a new word. Now the FIFO is not empty. There is one word in the FIFO, which is at address location entry 3. Okay. Now again, I am asserting a read signal. That data is also read. Now the FIFO is empty. Okay. Now let's consider. Now the address pointer has rolled back. That means this is 00, 01, 10, 11. But since we have used 3-bit information, the address pointer would look like 000, 001, 010, 011. Now it has wrapped back this at this point of time, wherever my cursor is, this address would be 100. Basically, this MSB bit, this bit number 2 would be 100 now. Okay. Ideally, we will be using only the 2 bits to address these locations. That extra bit, the MSB bit, we will be using to detect a full condition. Okay, let us explain now. Okay, now the read pointer is pointing to entry 3. Okay, but write pointer is pointing to entry 0. So I have written one more word in entry 0. Let me write another word. See, read is not getting advanced. Basically, no read is happening, but writes are happening. Now entry 1 is written with another word. Entry 2, another word. Entry 3, another word. Though both the write pointers and read pointers are at the same location, this does not mean the FIFO is empty. Correct? Because the pointer has wrapped this 2 down to 0 value is 0, 1, 1. But this write pointer address is 1, 1, 1. Okay, so this is not an empty scenario. This is a full scenario now. Okay, so now let's see a full. Okay, the write pointer, the number of bits that you want to address, that you need to address the number of entries, that both the write pointers and read pointers should match, and if the MSBs are different, that indicates a full condition, which is now the ideal scenario. My LSB 2 bits 1 down to 0, bit number 0 and bit number 1 of the get pointer and bit number 1 and 0 of the put pointer, both are same. Both are pointing to 1, 1. Here also 1, 1. But the MSB bit, in the case of read, it is 0. Whereas in the case of write, it is 1. Both the bits are different. This indicates full condition. The get pointer 1 down to 0 equals to put pointer 1 down to 0, and the MSB bits are different. Yes, then it's a full condition. This is the reason why we use one extra bit to detect a full condition. Basically, this is a widely used scheme across industry to transfer a data from one clock domain to another domain. Basically, the fundamental concept here is you will have one extra bit which is used to generate this empty or full status, and the other remaining bits will be used to determine which location. Okay, that's what is explained here. Put pointer n down to 0, basically a write pointer, and get pointer n down to 0. Basically, these pointers are nothing but counters. Okay, these counters acts as an address, acts as an address generator. Basically, you have a logic called as write control logic and read control logic, and this memory element. All this put together, we call it as Q or a FIFO. Okay, and you need n number of bits required for the entries plus 1. Okay, the extra bit or the extra upper bit is used to determine pointer wrapping. Basically, the fundamental concept here is if the pointer has wrapped same number of times, it is empty. Only if the write pointer has wrapped and it has hit the read pointer with the MSB bit different, it indicates a full condition. So this is typically how the data and address gets transferred from one clock domain through another clock domain, a kind of small scheme. Say you are in clock domain A where you are sending a data. Okay. Now this data, basically this load, which is nothing but a control signal, a kind of put information. Okay. This is a kind of write enable signal or a put signal. Okay. Now this is a pointer, which is nothing but a put pointer or a write pointer. Okay. This from this the data which you want to transfer, before it gets transferred to the domain, the address pointers are gray encoded before the address pointers are domain crossed. Okay, so that's what it's explained here. Initially, we are loading A, which is nothing but your content, then the pointer A. Okay, the pointer A is clock crossed, and then it is synchronized to pointer B, which is clock domain B. And then this read pointer, this unload is read portion, load is write portion. Now you see here the unload pointer, basically the read pointer is compared with the synchronized version of the write pointer to check whether the FIFO is empty or not. Okay, so this you compare for empty, these two, this and this. Okay, based upon the comparison, if both the pointers values are same, then you can say the FIFO is empty. That is what we are showing here. Now, once you have compared, then you can assert the empty flag or deassert the empty flag if it is not empty. Then while reading, you are reading the data. Okay, the addresses are gray encoded before it is transferred to the destination clock domain, which is in this case, sorry, to the source clock domain, which is sender domain, in this case, clock domain A. So if you see here, now you are unloading a pointer. Basically, this read pointer is now synchronized to clock domain A. You see, this read pointer is originating in clock domain B. This read pointer is gray encoded, and the gray encoded pointer values are synchronized to clock domain A, and this synchronized read pointer value is compared with write pointer for a full condition. So basically the synchronized version of the read pointer compared with the write pointer, if both the values, if the pointer values are same and their MSB's condition. Okay, this is what typically how the queues FIFOs operate. Sorry, let me go back. This is how typically how the FIFOs operate. Basically, the fundamental concept here is that you have an internal address generator module, which are nothing but write pointers and read pointers, which acts as a address location to access the particular storage location. These address pointers are gray encoded before it is sent to the destination clock domain. In the destination clock domain, they are synchronized, then they are compared for empty or full conditions to generate a full or empty status flags. In the previous slide, I told we are using gray bit. Why? Okay, because gray codes has a property, I think I have, yeah, gray codes have a property where only one bit changes at a time. If you see, for example, let us consider instead of gray encoded pointers, if I use binary pointers, what will happen? Let's say in binary, every bit changes there is more than one bit changing at a time. Say for example, if I want to transfer from 0, 1 to 2, so this 0 becomes 1 here and this 1 becomes 0 here. Both the bits are toggling. What happens during domain transfer? Instead of this becoming 0, if this become 1, by mistake, I would be pointing to address location 3. Ideally, I should have pointed to address location 2, but by mistake, I have pointing to address location 3, which is wrong. If by mistake, instead of this 1, 0, if it has become 0, 0, instead of me pointing to address location 2, I would have been going and pointing back to address location 0, which is wrong. This is what we call as data incoherency. Though you use a synchronizers, you cannot guarantee that you will get a reliable updated value. For that reasons, we recommend we use gray code scheme. In gray code scheme, only one bit will change at a time. That means that bit can become whether it can take a new value, which is 1, or it can take a old value, which is 0. That means either you will go to a new correct address or you will come back to the correct old address. You will not go to some wrong address. That is ensured by gray encoding scheme. This is the reason why we use gray encoded pointers. Okay. Now, so far what we have discussed is asynchronous clock domain crossing, where we don't know the phase and frequency relationship of the clocks. Now, and there are typically some schemes which are used widely to do a clock domain transfer. Okay, now let's talk about synchronous clock domain crossing, where synchronous means I know the phase and frequency of the clocks. Basically, the clocks that originate from the same source or from the same derivative version, they are called as synchronous clocks. Let's consider in this case, I have this clock and this read clock, RD underscore clock. Both are synchronous. That means both are coming from same source. Okay, though the frequencies may vary, but they are synchronous. Now I am writing a data into this FIFO and I want to read the data from the FIFO. Now, in this case, we cannot say that I don't want a FIFO. Though my clocks are synchronous, there is no, you need to watch out for some scenarios where you may require a FIFO. One example is if write and read clocks are synchronous and are of same frequency. Okay, Okay, let's assume this is also 100, this is also 100 megahertz, 100 megahertz. Do I still really need a FIFO? Yes. If data can, let us consider the scenario, if data can be read by the read side logic as soon as it is written. Say you have written some data A, immediately the read module, the read logic comes and reads it, then in that case, you no need to have a FIFO. Okay. If read is performed only at certain intervals, say for example, I will start reading the data, only 10 data is stored in the FIFO, then only I will read. In that case, you need some storage mechanism, which is a FIFO. Okay, if read can be performed only during some specific intervals, then you need a FIFO to store the data temporarily until it is read. Okay, what happens if data is continuous? Eventually your FIFO will become full. You cannot build a FIFO which is having infinite depth. You need to bound by some constraints. Okay. By the way, remember FIFO is costly in terms of logic area, in terms of power, in terms of verifying the functionality. Okay. If your FIFO does not behave the way it's supposed to behave, then no point in adding this logic. Okay. FIFO is a costly affair, but it's a reliable mechanism which can be used to reliably transfer data from one clock domain to another domain. So if your data is, if your input stream is continuous, then you cannot build an infinite depth of FIFO. You need to bound by some constraints because these are memory elements. Okay, your RAM is costly. Okay. Now in such scenario, you need to have a mechanism to stop incoming traffic. Whoever is sending the data, he should have some small buffer within him, or he should have some kind of control logic where he can store the data temporarily for a certain period of time. Then he can pump the data to you, which you can pump to the next module. This is how data propagates from one module to another module till and it gets processed in each stage till it hits the output. Okay. So if data comes continuously, then you need to have a mechanism to stop the input traffic. Okay. A quick recap of what we have discussed so far. Okay, we talked about the synchronous and asynchronous clocks, which is nothing but synchronous. You know the phase and frequency relationship of the clocks. Basically, the clocks originate from the same source. It can be from the same PLL or it can be from the same clock generator, whatever it is. Whereas in the case of asynchronous, the clocks are originating from two different sources. You don't know the phase or frequency relationship. This is how today's SoCs are designed. You will have enough of clocks, lot of clocks in your designs. Every design which has more than one clock, a proper synchronizer structure should be used to domain transfer the signals. For asynchronous crossings of 1-bit information, you can, okay, there are two properties which you should watch out. First thing is the async signals should be glitch free. You are not supposed to feed a combinational output. You should register the combinational signal using a flop, and the flip-flop version should be given to the synchronizer, should be fed to the synchronizer. Okay, a widely used method to synchronize 1-bit information is 2-flop method. Okay, but it will not work always. Think properly before you use. Okay, asynchronous crossing of bus. If you want to transfer a wide data bus or wide control bus information, how you do? These are the three schemes which we discussed. Mux-based synchronizer, where you ensure that only the enabled signal coming from the source domain is synchronized to the destination clock domain, and then the mux when the mux is enabled, the source should keep its data constant so that the destination can sample it reliably. Handshake synchronization. This scheme is very powerful and very robust, but only thing is it has some small drawbacks, which is latency, which degrades the performance of the circuit. Okay. Another powerful scheme is FIFOs, generic queue. Okay. You need to ensure that the FIFO depths are the number of entries, that how many entries you want, so that FIFO does not get overfilled or FIFO does not become empty. So that FIFO calculation and the pointer crossing should be handled properly. If you don't calculate the FIFO depth required properly, then it is high chance that you will overflow soon and you will lose the data. Okay, if you lose the data, then your downstream logic will go for a toss, which will break the functionality. So think before you decide which method to use. Okay, these are the widely used methods and proven techniques, proven robust techniques, which is used across industry to build SoCs, where we want to transfer, where we want to domain cross the signals. Okay, a quick cap on this. In summary, whatever Padmanabhan has discussed today morning, don't take timing analysis for granted. Okay, whatever design you are building, if your design does not meet timing, then no point in building it. Okay, you have to apply proper constraints and you have to ensure that your design meets the required setup and hold times. Then only it will work properly in the silicon. Okay, then only you can give it to a customer to build this application. Then only it will go to our production in the market. Okay, understand the scenarios and think about your constraints. Okay, before applying constraints, think, okay, whether whatever constraint I'm applying, is it correct? Okay, if you really want multi-cycle path, think, is it really a multi-cycle path? Can I optimize this circuit? Can I do a computation in single cycle instead of me giving a multi-cycle path? Okay, if you think that these two clocks are asynchronous, ensure, talk to the clocking person or whoever has built the clock network, talk to them, ensure that these two clocks are really asynchronous, then you apply false path constraints. Okay, understand the digital logic electronics timing fundamentals so you can design a system, a functionality reliably on FPGAs or ASICs. Okay, all of these basics is one thing, your binary digital logic design. Okay, zeros and ones. Okay, be thorough in it, understand how it works. Okay, go till the transistor level. Okay, go till the gate level circuit. Okay, do a paper design. If you are trying to build some logic, some circuit, try to implement it in using a gates. Then you try to understand how the data travels through each gate, estimate the try to understand the functionality first, then perform your synthesis. While performing synthesis, then apply timing constraints. Okay, then see how you are, whether you have met your timing goals. I think this is, yeah. These are some of the reference documentation for the which the audience can refer. Basically, the first link looks like it shows it's a user guide for timing analyzer. The next one, design optimization guide. Basically, optimization in the sense, you can, I think it will talk about some of the optimization techniques which can be used from while you are building a design. Okay, some performance design handbook, some quick start tutorial on timing analyzer. And these are some of the online training links which you can watch out if you have some doubts, so that your doubts gets clarified. How to launch the timing analyzer GUI, how to apply constraints, how to generate the reports again, how to analyze the design again, whether it has met the required timing constraints or not, all those things. Then some prime time integration and reporting, then how to write SDC constraints, all those things. Yeah, I think Paddy, you want to take over, Paddy?
Yeah, that's fine, Bhaskar. Yeah, you have explained it. That's fine. Thank you.
Yeah, I think
Thank you,
we have
Bhaskar,
some more slides, Paddy? Yeah.
That's
So
all,
I think with this, yeah. So I think with this, we have covered the topics what we thought to discuss with you people today. Feel free to raise your questions if you have any doubts. Let's try to answer them either online or offline. Okay, if you have any questions, please send it to the respective. Please coordinate with your respective coordinator. We will try to answer them. Okay. Thanks everyone for patiently listening to us, and hope you have learned something new today. Thanks to the team here for giving me such an opportunity to share my knowledge. Thank you.
Thank you so much, Bhaskar, for the wonderful talk.
Yeah, on behalf
Paddy,
of
can I
E&ICT
stop
Academy,
presenting?
IIT Guwahati. Hello, am I audible?
Yes, you are.
Yes, madam, you are audible. Yeah.
Yes. Yeah, yes. So on behalf of E&ICT Academy, IIT Guwahati, and all other academies and our coordinators, we would like to thank you, Bhaskar sir, for such a wonderful talk. Thank you so much. I could see that Q&A, most of the questions have been answered by Padmanabhan sir. Thank you so much, sir, for your prompt responses. I think participants would have found it very useful. So with this, we come to the end of our day 2. The slides and all the material will be made available to you by the evening in the same drive link. Also, there is a file in the drive known as important announcement. Please keep checking it for further announcements. Regarding MCQ, we will be having an MCQ on Thursday from 1 p.m. to 2 p.m. There will be 50 questions comprising of 1 mark each, and you will be given 60 minutes. The timing, we will be very strict with the timing, that is from 1 p.m. to 2 p.m. and no further request for after the time is over for doing MCQs and other things won't be entertained. So please make yourself available on Thursday from 1 to 2 for doing the MCQs. Thank you so much. If you have any doubts, you can post in the Q&A, or tomorrow also, if you have any doubts, you can ask. Tomorrow the session starts at 9:30 a.m. So see you tomorrow. Thank you, everyone. Thank you, Bhaskar sir. Thank you, Padmanabhan sir. Thank you so much.
Thank you all. Thank you, everyone.
Thank you, everyone. Syllabus for MCQ. Syllabus is whatever they are teaching you till day 4. Everything will be there in the MCQs.
Correct, correct. So till the 4th day afternoon, what is covered, that would be asked by 1 o'clock. Yeah.
Yes. Yeah. Thank you. So you are free to leave. I am ending the event from my end. Thank you.